بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome everyone to our first KAUST Health Safety and Environment webinar on radiation protection and safety in research, industry, and medicine. I hope everyone is excited as I do right now. And as Marcus told me today, it's a lovely day. And also I'd like to welcome five of our guest speakers who are joining us here in KAUST. And two will present from Riyadh because they were busy, they couldn't make it. Thanks everyone for joining, and we hope to enjoy this interesting event. I'd like to introduce our first speaker, Mr. Eric Talley. He's the Health Safety and Environment Director. Please, Eric.
Thank you, Mohammed, and good morning to everyone, and welcome to King Abdullah University in Science and Technology from myself as well as our president, Dr. Tony Chan. So you're participating in the first meeting on radiation protection and safety in research, industry, and medicine, hosted by our HSE department, and you'll also have an opportunity to learn a little bit more about KAUST and HSE in a short while when Marcos Aguilar, our acting research safety manager, gives a presentation. So when we started on this endeavor, we did not know how many people we would have participating, and it ended up that we now have over 800 participants coming to us from 10 different countries, ranging from Albania to the United States of America. So it's really great to see that we have this level of participation, and we would like to have you here to our beautiful campus, but obviously with COVID-19, large gatherings are very challenging at this time, so we can postpone that to a future conference. But I have to say, I'm feeling really optimistic from the COVID-19 perspective. We in Saudi Arabia are maintaining a very low positivity rate. Millions of our Saudi nationals as well as expatriates have either been vaccinated or well on their way to vaccination, and really seeing the sense of new normal. So hopefully not too long in the future we can invite you to our campus as well. But we are fortunate today to have a number of our presenters here. And what I especially like is that we have a very diverse group of presenters. So we have two representatives from our government, the Ministry of Health, as well as the Nuclear Regulatory Commission, the Nuclear and Radiological Regulatory Commission, excuse me. We have participants from the medical sector, the health sector, so King Faisal Specialty Hospital, and then we have a number of our sister universities as well, from King Abdulaziz nearby in Jeddah, Jazan, KAUST, sounds like KAUST, but with the C, and King Saud University. So one thing that our president places a lot of importance on is what he calls impact. We are obviously an educational university, and we can be great internally, but with our primary mission of education, part of that is outreach as well. And so it's that external outreach of bringing all of us together to share information and resources. And so I'm very excited that we're able to do that together today. You know, as a profession in HSE and other related professions, we know that we all have limited resources, and as the saying goes, we don't want to reinvent the wheel if someone has already invented it. So it's great to see that we can share these various resources with each other and be able to help each other out. So lastly, I want to give a big thank you to Mohammed Bahmed, who is our radiation safety officer, but also the principal organizer of this event, as well as our entire research safety team that has spent a ton of effort in making this happen, including Marcos Aguilar, Lamont Jones, and Venkata, our admin assistant. Thank you very much. It's on.
Thank you, Eric, for the introduction address, and welcome everyone to KAUST. To show you a little bit of KAUST, and as Eric was saying, we wish all of you joining us online will have been able to make it today here with us and enjoy this beautiful day. We're gonna play a little video from our university. So I hope you like it.
Hello, everyone, again. Since the beginning of COVID-19 epidemic, we are forced to wear face masks, and you're used to it so that you forget it. You forgot to remove it when you speak. And they told me that when I stand at the podium, I have to remove my mask. So I forgot it. I forgot first time to remove it. So here I am. So now let me introduce you to our second speaker in this event, Mr. Marcos Aguilar. He is our research safety acting manager, and also he is a safety specialist lead. So please, Marcos.
Thank you, Mohammed. Let's go back here to the presentation. Just a minute. And here we go. Thanks for the introduction, Mohammed. And thank you very much, all of us, all the people joining us today. I wanna start with Salam alaikum, Ahlan wa sahlan, marhaban bik, fi Jamia Marek Abdallah lil Alyum wa Teknia. Welcome everyone. I'm gonna be acting as point of transition. We're gonna continue talking a little bit about KAUST. Then we're gonna talk about what we do in HSE. And the title of my presentation is Research Safety here at KAUST. So I'm gonna share some of the programs, some of the systems that we have in place to keep the laboratories and research safe. Also, big disclaimer, all the pictures that you will see here today, except one, are all with people without wearing face covering. This is pre-COVID era. For those who don't know where we are in the map, KAUST is located 80 kilometers north from Jeddah in a beautiful coastal area near our fishing village nearby, Thuwal. KAUST was founded in 2019 with the vision to aspire to be the destination for scientific and technology education and research, to address global challenges and serves as the beacon of knowledge, to integrate this interdisciplinary research and graduate education, and to connect science and engineering, with a special focus on areas of global significance, as you can see in this slide: water, food, energy, and the environment. To tell you a little bit more about KAUST, it's a small place, but it's also a big place. This is a portion of the KAUST land. If we talk about land extension, it's 36 square kilometers. 36 square kilometers could be the fifth smallest country in the world. Around the campus area, we have town center, the community, the research and technology park, the innovation cluster, and also the services and utilities that serve all these community, where we approximately now, we live inside KAUST, around 7,500 members. I also would like to speak about the 3 academic divisions here at KAUST, starting with BESI, the Biological, Environmental, and Science and Engineering, offers top degrees in the areas of bioscience, biotechnology, environmental science, marine science, as we have the beautiful Red Sea as one of our largest laboratories, and plant science. In the division of computer, electrical, and mathematical science and engineering, well, programs such as computer science, applied mathematics, electrical, and computer engineering, to just name some few. In the next division, physical science and engineering, we have degrees and programs, masters and post and doctoral degrees in applied physics and chemical engineering, chemical science, earth science, energy resources, material science, and mechanical engineering, to name some of the programs in this division. These divisions, as I was saying, they act and are organized to have a lot of multidisciplinary and cross functions. So to give you some of the examples of the biggest centers, research laboratories that we have here at KAUST, just to name a few: the Red Sea Center, the Water Desalination, Advanced Membranes, Catalysis, Solar Center. These are some of the centers that are here at KAUST. As you can see, these are very specific to the areas of global challenges, as I was mentioning in the beginning: food, energy, water, and the environment. Another important group in the university are the core labs. The core labs are a user facility providing solutions to KAUST and the Kingdom. They're state-of-the-art facilities with cutting-edge technology and staffed by experts providing solutions to our researchers and also to some industries and companies. Some of the examples are Analytical Core Lab, Bioscience, the Coastal and Marine Resources, the Plant Growth Core Lab, Imaging and Visualization, the NanoFab, the Supercomputing Laboratory, the Visualization Lab, and the workshops. These all to provide support to our researchers and also to the Kingdom. Well, how to support all this? Well, it's not only the core labs, the research centers, there is more. Individual faculty, they also have their laboratories. In total, I could say that we have around 160 laboratories that are in full operations, up and running. They occupied an area that it's quite large. It's 60,000 square meters of laboratory space. You would say, how to support all these very diverse and specific areas of research? Well, we have a great team behind. In KAUST HSE, we are a service department, and we have services from the fire station with a full-fledged fire station providing support to the campus and also the community. A team that takes care of the residential and facilities and all related safety issues within the utilities or the community. Emergency management, also a team ready to act and have the necessary plans to do all the emergency planning and preparedness, and of course the response. The environmental protection team, looking after our beautiful environment around us with environmental monitoring, air quality, and as well a lot of community engagement. And now, moving on to the topic of my presentation, we're gonna cover what the research safety team does. And the research safety team, it's a dedicated team here at the King Abdullah University of Science and Technology to look after the laboratories. We also have a team of experts and safety professionals in different fields. So this is some of our current specialists in our group that we run different programs and systems. Programs such as the biosafety program, the lab design, the laser safety, chemical safety program, the industrial hygiene, and radiation safety, the reason why we are here today. I want to use the next minutes during my presentation to share some of the programs that have worked very well with us, to share some of the good practices, and also some of the systems that we have implemented and work really well to keep laboratories safe. We work a lot on the prevention, so we're going to start talking about laboratory inspections. We have a solid and robust laboratory inspection program with biannual inspection. So we go to the lab twice a year and we inspect every single corner, even we open drawers, cabinets, we inspect thoroughly the laboratories. When we do an inspection, it's an announced inspection, so laboratories are ready to receive us. And we look at areas such as general safety, chemical safety, biosafety, electrical safety, quite important, housekeeping, hazardous waste. Oh, we're back, sorry for that. Hazardous waste, and just the general state of the laboratory. It's an online reporting system where our researchers and users can see the results of those inspections. And to support this program, we also have procedures in place, like the laboratory reinspection criteria. If labs have increased a number of actions or findings, we'll go back and reinspect them. If things are not fixed, then we can trigger our procedure on suspension of lab operation. We'll give them a time to fix their lab before any incident happen in that lab. So we work a lot of prevention. We rely a lot in our lab safety representative. This is a quite successful program that I want to share with you today, where we have extended network of safety eyes and ears that help us on the day-to-day operation. Every laboratory here at KAUST is required to have at least one lab safety representative and a backup. And those LSRs, those lab safety representatives, help us to raise awareness, help us to communicate our updates, help us to be the focal point of contact for safety, and promote and communicate our initiatives and new programs. They help us also to conduct self-inspections and provide assistance during emergencies. Also, they participate on the lab safety forum that we host 2 or 3 times a year. Another important program that also we have very good participation is the lab safety training. Anyone who wants to enter a laboratory here at KAUST, before starting any experiment, they need to take 3 required courses: general lab safety, hazardous waste, and incident preparedness. Those are the 3 required courses, but we also have hazard and lab-specific training that we offer, depending on the type of lab, depending on the hazards that are in each laboratory. Then they can use our system to trigger that in training that will be necessary for them to take. Among all those courses, we have now a good catalog of more than 50 different type of courses that goes from liquid cryogenic safety, flammable liquid safety, compressed gas safety, and of course, radiation safety training. These courses are offered live and as well as online courses. We don't stop there. We go the next mile, and we also want to encourage those that just take the required courses to broaden their knowledge in safety. So we want them to go and take the next step and achieve what we call the research safety certificate. A quite good certificate to have, but it's also a little bit difficult to get. Lab users will have to get 5 required courses plus 9 other elective courses. And when they complete that, they can just email us their previous training certificates, and then we'll grant this beautiful research safety certificate that they can also use in their next employers, or just add into their curriculum, and will show how much effort and time they put into safety. One more program that I would like to share with you today, and that also help us a lot, is the building zone matrix, or the building point of contact. Before, we have our specialties: radiation, biosafety, laser, lab design, and we try to cover all the campus at once. So we were all scattered everywhere, trying to respond every single call, depending on whether it's bio, radiation, laser. We tried to change that approach to have a more customer-centered approach and serve our buildings in a better way. So what we did is the building point of contact. Each person in the research safety team is responsible for 1, 2, or 3 buildings. And then with this, we built a better relation with the labs, the centers, the users, the professors that are in this building. So we split the building into zones and into buildings. This helps us to foster better relations, provide better communication, and better customer service. Now, also, we are a university, and we have a lot of turnover, a lot of students that come and go all the time, visiting students, visiting scientists. One of the things that we found out is that we need to participate as well with a quick inspection as part of the departure clearance, making sure that when a researcher leaves, they remove their waste, remove their samples, and bring back their chemicals to the original cabinets where they originally stored. So this also helps us. I'm sure if you're joining us from other universities, you have similar problems when people leave. So that program helped us a lot. One last program that I would like to share with you is the lab safety recognition. We like to celebrate, we like also to recognize those individuals and teams that are doing great on safety. They're doing above and beyond. And we also want to bring this culture of safety culture to foster this environment that values safety by promoting safe behaviors. So we have 2 awards that we started since 2016 and we do every year. One is the team award and then it's the individual awards. So this is just some of the programs that have been successful in our group and I wanted to share here with you today. If there is any questions, my colleague Lamont will address them, I can answer them. And also this will help also as a good introduction now that we're going to go into our topic here today that is radiation. So the next speaker will be Mohammed Mahmoud, the radiation safety specialist from this group. Any questions from the audience? We also have a wireless microphone or something from online. All good? All right. So thank you so much. Thank you for your time. Enjoy the day. Thank you so much.
Thanks, Marcus, for this beautiful introduction to lab safety program. And today the weather is very nice in KAUST, and I think what make it beautiful is you joining all of you joining us in this webinar. We have more than 800 registrants, and now I think we have more than 274 people online with us right now. So thank you all for joining us, and I hope again you enjoy this event. Today I'm going to speak about the radiation safety program at KAUST. The program is not that big, but it has a lot of responsibility that it won't be covered within my time limits. It will take more than 2 hours. And I think Lamont will not allow me to go beyond the 20. He's like our timekeeper, and he will ensure that everyone will keep his time. So I'll stick to my time. Therefore, I'll just choose some of the most important tasks or responsibility that we are doing in KAUST, which is the licensing and permits. I'll talk about training. I will talk about how we control radioactive material in KAUST and how we record keeping and documentation all our work, and how we do radiation monitoring. I think because we have many people joining us, so I'm not sure about the background of the people. So I think some of you have very advanced knowledge about radiation, and some have medium knowledge or little knowledge, and maybe some of you have no knowledge. So I'll just go ahead quickly and explain what is ionizing radiation. So radiation is a general term that includes many things like radio waves, microwaves, visible light, laser, gamma rays, and X-rays. This is a general term. However, we are talking about ionizing radiation. Ionizing radiation is radiation in the form of particle or electromagnetic radiation that have enough power or enough energy to remove a tightly bound electrons from an atom. And this will cause the atom to become charged or ionized. I'll use this one. This is, I think. There are 4 types of ionizing radiation. We have alpha particles, and alpha particles are very dangerous if it was ingested, but it has very low range in the air, and it can be stopped by like a thin paper or by the dry, by the first layer of the hand. Beta particles are electrons or positron, which is charged particles, and they have low ionizing density. Also, we have gamma rays and X-rays. They are the same, but gamma rays originated from the nucleus, and X-ray originated from the atom. And they have low ionization density, but high penetrating power. And then we have the neutron beams, which is uncharged particles and have very high ionizing density. So I think this will be enough to introduce ionizing radiation. And please, if you need more information about this, you go ahead and read more about it. So we'll go now with our first poll question. This will make sure that everyone is awake and joining us. So first question will be, if radiation can really give you a superpower, what would you choose? So choose the right, there is no right answer, but choose what you like. Laman, can we see the results? Or? Okay. Can we see it on the screen or just? No. If you could project the answer. All right, so 28% choose to have the power of mind reading, and 33% choose to be invisible. 26% like to fly. They want the power to fly. And 24%, they said, I already have a superpower. So I wonder what kind of superpower they have. Anyway, this is just a funny question. It's not a serious, but we'll have more serious question later. But this is just to keep you with me. So Radiation Safety Program. The Radiation Safety Program provides oversight, ensure compliance with national regulations, and promotes good health, well-being, and safety for faculty, staff, students, and visitors connected to the university. There are key components to KAUST Radiation Safety Program. The first component is the Institutional Safety Committee, the IRSC, and the Radiation Safety Officer, and the Radiation Use Authorization Holder, and the Radiation Worker. I'll explain each one of these in a moment. So first is the IRSC, Institutional Radiation Safety Committee. This committee consists of 5 members, including the Radiation Safety Officer, and they are appointed by the responsible official in KAUST. And it oversees the radiation safety program in general and authorizes the use of radioactive materials in the university. Also, the IRSC authorizes the use of regulated X-ray producing equipment. Any equipment above 50 kV, it will be approved by the IRSC. If it's less than 50 kV, it will be approved by the Radiation Safety Officer. Also, they review incidents involving radioactive materials, set policies for the use of sources of radiation at KAUST, and gives general supervision to the implementation of those policies. They meet every 6 months. So we have 2 meetings per year. We discuss all aspects and all issues related to radiation safety program. The radiation safety officer is appointed by the KAUST to manage the radiation safety program. The radiation safety officer is licensed by the Nuclear and Radiological Regulatory Commission, the NRC, and the license is valid for 3 years. The RSO is available to advise authorized users and radiation workers on radiation safety and regulatory compliance issues to provide the following service. So first, the RSO will maintain the validity of radiation license and import permit. Our general radiation license is valid for 5 years, and the import permit is valid for 1 year. So the radiation safety officer need to make sure that these licenses are valid, because if it's expired, then we cannot do or perform any radiation work at the university. Also, the RSO supervise all radiation activities uses. Also, he or she provide training to radiation workers. Also, the RSO personnel also provide dosimeters to radiation workers, provide consultation, also perform laboratory radiation surveys, also investigate incidents, spill and contamination management. Also, he manages the radioactive waste and approve and control radioactive materials. Now we have the radiation use authorization holder. So what is the radiation use authorization holder? Any person or principal investigator or researcher who would like to conduct research using radioactive materials or use radiation producing equipment must apply for a permit, or we call it radiation use authorization. And this radiation use authorization, or the application of the radiation use authorization, must be approved by the IRSC or the radiation safety officer. And for radioactive materials, it must be approved by the IRSC. For radiation equipment, it could be the IRSC or the RSO, it depends on the energy of that equipment. Now, to approve the radiation use authorization, we have to study or assess the risk behind the use of this material or the equipment. So we identify the hazard and then who could be harmed and evaluate the risk, and also to check if there is a finding on this applicant, and then review the whole application, and either we approve it or we reject it, and until fixing the issues that with this application. Radiation workers, a radiation worker, anyone who uses radioactive materials or radiation producing equipment. And before using or working on radiation equipment, the radiation worker must get the proper training on how to use this equipment, and also on radiation safety in general. And also, he or she be familiar with the relevant procedures of the radiation safety program, including the radiation safety manual. We ask all radiation workers to read the manual and understand all the policies. And if they have any question, to return back and to the RSO for feedback or for an answer. Okay, so I'll talk about now the license. KAUST has a general radiation practice license in the field of research and education. So there are many types of radiation license. There is a license for transportation, there is a license for medical uses, and for industrial uses, and there is a license for research and education, which we got from NRC, and it's valid for 5 years. And this license listed all allowed radioactive materials that we can possess within 5 years. And also it listed radiation producing equipment that is above 50 kV. Now, the other permit is called import permit. Import permit is very important document that is issued by the General Security as a requirement by law to import radioactive materials. The import permit valid for 1 year. And believe it or not, it takes 6 months or 4 months from the first day you apply for it till you get it. So every 6 months, you have to apply for another import permit. If you don't have import permit, you will not be allowed to import any radioactive materials. So far, we have ordered or imported several radioactive materials. We have phosphor-32, tritium, carbon-14. Tritium and carbon-14 are long-lived radionuclide. We also have sodium-22, which is a gamma radiation. We have chlor-36, and we have also uranyl acetate, which is a compound of uranium-238 and uranium-235. Right now, we are using only the phosphor-32, which is short-lived, and the tritium and the carbon-14 in our radiation core lab. Now we go to the training and education. All users of ionizing radiation must have a level of training and awareness of hazard before working consent. This is very important because the aim of the training is to provide an introduction to the legal requirements and the radiation safety aspects. And as they said, teach people good and will do good. So if you don't train the radiation worker, you don't expect them to do perfect work in the lab. So you have to make sure to train the people how to deal with radioactive materials, how to deal with the X-ray machine before you allow them to enter the lab and do their work. At KAUST, all our courses, most of our courses are online training courses. So you can log in and train at any time. Most of our courses take only 1 hour to complete, and it has the quiz at the end of the course. And there is like a passing score of 80 out of 100. If you don't get 80, you have to repeat that course several times till you get it. So the first course we have is the radioactive material safety training, and it is aimed toward those researchers or users who want to use radioactive materials in their research. The second course is the X-ray analysis safety training, and it is for those users who want to use XRD, XRF, or irradiator in their work. And we have the third course is the scanning electron microscope and the transmission electron microscope safety training. We have many users who are using SIM and TM in their research. Also, the last course is the Z-Portal safety training. The Z-Portal safety training is aimed toward security personnel who are operating the X-ray scanner at the gates of KAUST. In KAUST, at the gate, we have X-ray scanner that inspect cars and passengers in the car for any security for security purposes. And right now, it's not in operation because we are applied for a license and we're waiting for a license. And we hope General Mohammed Farran expedite the process of the license. But this training is still under review, and once we finish it, it will be posted or will be online for the security personnel of KAUST. Now we have the second poll question. Which of the following is not ionizing radiation? I hope everyone will get this one right. It's very simple. 30 seconds. All right, so 20% answered cosmic rays, 81% microwave, 5% X-ray, 10% gamma rays. The right answer is microwave. Microwave is not considered as ionizing radiation. All right, so we move now to our third topic in my presentation, which is the control of radioactive materials. KAUST plays a very good role in controlling the radioactive materials to the degree that we decided in the IRC to contain all work of radioactive materials in one place. So the core lab established a special core lab for radiation work. We call it Radiation Labeling Core Lab. All work with radioactive materials are contained in this lab. That's why this is how we control everything. In KAUST, we have like more than 160 labs. So if we allow every lab to use radioactive materials, it will be difficult to control and to know what's going. So we contain all the work in this lab. And not only that, we only allowed one person to order radioactive materials. So only one person have the right to order, or two persons actually, the RSO and the radiation safety specialist who manage the radiation core lab. They are the ones allowed to order radioactive materials. So also, once the radiation safety specialist at the core lab raised a shopping cart to order radioactive materials, it will come to the RSO. RSO will view the cart, will view the order and check or match the order with what we allowed in our license and what is allowed in the import permit. If everything is matching, then the RSO will approve the cart. So let me talk about the use of radiation. So what is the sources? Oh, all right. That said 5 minutes. Sure. So what is the sources of radiation in KAUST? So in KAUST, we have 7 sources of radiation. So first is unsealed radioactive sources. And we have the sealed radioactive sources. Sealed radioactive sources are sealed sources that came incorporated in equipment, like the liquid saturation counter, which has barium-133, and the gas chromatographer, which has nickel-63. And we have X-ray irradiator. We have one X-ray irradiator for animal research. And we have several X-ray diffraction and X-ray fluoroscopy. And we have transmission and scanning electron microscope. We have a lot of these. And we have 3 X-ray scanners installed at the KAUST gates. Now, as I said, the Radiation Labeling Core Lab is the only lab that allowed to use radioactive materials in research. And of course, it was the plan that if everyone was here, we'll take them a tour and show them the lab. But however, Augustine Essel, who is managed and supervised the lab, provided me with some pictures. So as you can see, this is a several picture of the lab. On the door, there are the signs of radiation sample. And the name of the lab is Radiation Labeling Core Lab. It has storage for radioactive materials, and these storages are locked and secured. Also, they have 2 advanced liquid saturation counter. Also, the work there is a designated area in the lab where people work with radioactive materials. They are not allowed to work everywhere in the lab, but there is a designated area where to keep their work in so that they can contain the contamination, because they are using with low quantity of radioactive materials, and our concern is the contamination, actually, not the exposure, because we are using with beta particles. And they have also a fume hood that is designated also for only radioactive materials. Now, how we order radioactive materials. Augustine, who are managing the core lab, will take the orders from the BI. There are 5 research groups who are working in the radiation core lab, and these groups order different kind of radioactive materials, mostly phosphor-32 or tritium or carbon right now. And they will inform Augustine about their needs, and Augustine will raise a shopping cart with the information of the radionuclides. And the shopping cart will come to me, and then I have to evaluate the order and match the order with our license, and I approve it if everything is okay. And then we develop supply chain procedure. So we need to follow the shipment, the radioactive shipment from the source, from the supplier, till it arrives to KAUST, because this is sensitive material and you have to make sure it arrives on time, especially for short-lived radionuclide. We need to make sure that it arrived on time because it has short-lived, short lifetime. So the supply chain team do a very good work in. So first the procurement will issue a purchase order, and then they will inform the supply chain. The supply chain, they will contact the supplier, and then they start the process of delivering to KAUST. It has many steps. So when it arrived to Jeddah Airport, then the RSO and the customs and the general police will inspect the shipment there, and then we have a contract with one of the local authorized transportation company to deliver it to the lab. Also, we created something called radioactive materials tracking dashboard. This dashboard will follow the shipment from the source, from the approval till it arrived to the lab. It has the PO number, the expected date of arrival at Jeddah, the shipment delivery date. Also, it will show how many days it was delayed at the airport when it arrived. It will give you details about the shipment, the isotopes, the type, the supplier, and the user, which group ordering this. And then anybody can access and know the status of the shipment, where the shipment right now. All right, now radiation monitoring. I'll go fast to these because of time. How many minutes? Zero. Okay. So there are three basic principles of radiation protection: justification, optimization, and dose limitation. Justification is just when you want to use radiation, you have to balance or to weigh risk and benefit. So always, if benefits is more than risk, go ahead. If risk is more than benefits, then you need to stop and review your request. Optimization simply means that radiation doses should be as low as reasonably achievable. And this is done through exposure time. You have to reduce your time next to the source. So the less time you are exposed, the lower the dose of radiation you will receive. Distance, the farther away you are from the source, the less intense its effect will be. So if you double your distance from the source, you will cut your dose by 4 almost. And shielding, you have shielding, then that means you are reducing your exposure. We have also applied dose limits. There is dose limits that required by the NRC, which is for occupational 20 millisievert per year. However, in KAUST, we are using ALARA limits. So we don't allow anybody to exceed 1 millisievert per year, either a radiation worker or, of course, the public is 1 millisievert per year, but also the radiation worker should not exceed 1 millisievert per year as ALARA limit. Also, to keep doses in control and exposure in control, the radiation safety officer at KAUST conduct a radiation survey periodically or whenever needed to ensure that occupational and public exposure are kept below the regulator limits. We are using survey meters that are calibrated every year at at King Faisal Specialist Hospital. And we maintain calibration so that the reading is accurate and they are ready to use whenever we need them. Also, we use personal radiation dosimeter to those radiation workers who are working in the radiation core lab or also working with radiation equipment that have energy more than 50 kV. Alhamdulillah, most of the doses now is background actually, so we never get like any doses more than background. We didn't have time for the other question? Yep. Okay. All right, so record keeping. Record keeping is a requirement in our program. So we have records for radioactive materials inventory, we have X-ray equipment inventory, and we have survey meters, calibration record, dosimeter user doses, X-ray monitoring record, wipe and peak test record. So everything we do, we keep record in our cloud server and also in hard copy as a hard copy. Standard operating procedure, this is something we do in KAUST. Every task we do, we have to write the procedure, which is step by step how we do it, so that everyone who will do it will follow this procedure, and no need to wait for someone to tell him how to do it. So we have almost 19 standard operating procedures and safety guide in different aspects. We have survey meters calibration, SOP, we have personal radiation dosimeter, we have how to documentation procedure, radiation emergency procedure, reception of radioactive materials, general radiation license process. So everything we do, we have to write it down as SOP. Okay, our numbers, I'm almost finished. So far, alhamdulillah, we have 0 violation. We have amended our license 3 times. We have ordered 16 radioactive materials. We have 40 users with personal dosimeters. We have 70 radiation use authorizations. We have 74 radiation producing equipment, and we have trained 1,416 radiation workers. Our message is protection from radioactive materials contamination, X-ray exposure, and compliance with regulation is the priority at KAUST. This is our partners, the security, General Security, NRRC, Saudi Customs, and Government Affairs at KAUST, and Logistics Services at KAUST. Thank you, everyone, and I hope you enjoy the rest of the day. Thanks.
Okay, we have a 5-minute break now. We'll come back here. We start at 10:05 with the next presentation. Okay, don't log out. For those joining us online, please do not log out of the session. Just stay. Just a small break. We restart. Thank you.
Welcome everyone back. So our next speaker is Engineer Mohammed Farran. Engineer Mohammed Farran is the acting manager in the Regulatory Operations General Department and working for the Nuclear and Radiological Regulatory Commission at Riyadh. Please, Mohammed.
Thank you. So, hi everyone and good morning, and I hope you're enjoying the day, the beautiful day. I will start my presentation by thanking KAUST actually for organizing such a webinar. This as webinar actually support our main concept of public awareness. So it's give awareness for the public how the radiation protection is going on in the kingdom, and also give an understanding of how we handle it with the protections in the terms of any activity of radiations. My presentation will cover and will answer a main question, that's what is the national legal and regulatory frameworks. So at the end of my presentations, we'll have a clear vision about what is going on in the country. So the presentation have 3 pillars. First, we'll cover the legal framework and then the regulatory framework. And after that, a brief what is going on right now within the commissions. So by starting by listing some of the decisions or government decisions regarding the nuclear radiation activity, we're starting with the approval of national policy for atomic in 2018, March 2018. And also in the same dates, approval for creating our commissions, nuclear and radiological regulatory commissions. After that, in April 2018, the law of nuclear and radiations uses, and also the RICO liability law for civil liability for nuclear damage was approved on the same day. In 2019, there were an approval for using IAEA as a minimum safety requirements in the country of Saudi Arabia. The last decisions was in 2021 is a national policy for radioactive phase management. So there is like, from what I showed as a decision, there is like a questions before 2018 of establishing commissions. How the regulator, how the things was regulating in terms of radiation activity. This video actually gives you an overview about how moving the responsibility of regulating such an activity through the kingdom. The radiation application was used in 60, actually, starting in 60. And this responsibility of oversighting and controlling such harmful, maybe harmful use if going to something wrong. So this was controlling by several entity within the country. So let's enjoy the video.
The use of radiation technology in the kingdom goes back to the early 1960s and was used mainly in the oil and gas exploration activities, supervised by Ministry of Petroleum and Minerals. During the last 2 decades, the use of radiation applications grew in different fields, including medical applications. In 1985, supervision transferred to King Abdulaziz City for Science and Technology. By 2010, King Abdullah City for Atomic and Renewable Energy was established and was assigned to act as the nuclear energy program implementing organization, including nuclear regulatory aspects. The Saudi National Atomic Energy Project was approved and launched by the Saudi Cabinet of Ministers in 2017, resulting in the startup of the development of 2 nuclear power plants. The site specifications and first stage activities are underway at this time. The sector continued to grow, and by 2018, the Kingdom established the Nuclear and Radiological Regulatory Commission, NRRC, as an independent government body mandated for all nuclear and radiological regulatory aspects. The evolution of the NRRC is also in keeping with the ambitious developments of the Kingdom's 2030 vision and will contribute to advancing the Kingdom's national safety, security, and economic growth.
Right. So the question again, why we change it like many organizations to control it actually? Why establish NRC right now at that times? The question is that they were, these actually ministries or organization was controlling, but there were no strong or empowerments by legal instruments to enforce, to inspect, to oversight over the facility. So what has have been changed actually since 2018, and there is a national law that gives the authority to the regulator, the commissions, NRC, is to enforce, to have penalties and violations if there is any violations for any law or regulations or conditions within the license. So this is what have been changed as a major, the strength in oversight, having a penalty and having also the violations, Vince. Here you can see topics have been covered within the law, the licensing. It's prohibited for anyone in Saudi Arabia to use or possess any radioactive materials without having a valid license from the NRC. And also the covering of safety, security safeguards, how we can run it within the country. Transportations, including the import-export of radioactive materials. The emergency preparedness and response on a national base and also as a facility base. There is some professions on both sides. The waste management, what is the licensee obliged to do actually when we have the management of waste, radioactive waste. The inspection programs, and then as I mentioned, the maximum limits for violation and penalties. And I know all of us actually, and all of you have been working before 2018 in these fields, radiation fields. So I highly recommended everyone actually to go back and read the law and understand what is it actually, the rights of the workers and also for organizations how to license, valid license from the NRC or commissions. By the way, it's all published, the laws and also the charter of the NRC within our websites, NRC commissions. It's nrc.gov.sa. You can Google it easily. And I highly recommend it actually to read it. Here are some of that anyone's working within radiation protections should use this principle: justification, optimization, limitation. I will not explain it because Dr. Muhammad Bahmed have covered it in his presentations. I would like to say this one coming from international words. It's like obligations from the IAEA and also from the ICRP as a commissions. We are here in Saudi Arabia having said that in article number 9 in our law. So for us, in order to review the application, in order to give a license, we have make sure the applications meeting enough explanations that covering the practice cover or explain it enough informations to explaining these three principles. Moving to the charter of the NRC, we having three main activity or objective. First one is protecting the people and environment together. We understanding that the radiation application may be harmful if it's going wrong. So we are ensuring to protecting the people and environments and also meeting international obligations. In my presentation, I will show like list of international conventions and treaties. As a kingdom, we are party of, and we are there's obligations to fulfill that or compliance with. The last one is oversighting, which including inspections, enforcement if there is any violations. Here you can see the timelines, as I explained before, just as a figures. National policy in 2018 with the same seminar to or in the same times approval of the charter of NRC. After that, in 2019 February, Dr. Khalid Isa have been appointed as a CEO for the NRC, and we starting actual commencing as an independent regulatory, having its own financial and also capability as a resources in 2019 July. So by meaning of that, we are newly established, less than 2 years actually, starting to develop a new era of regulating and oversighting the activity. You have noticed from our logo, there is 3 orbits, and there is like a story behind that. Each orbit representing one of the S that the IAEA explain or having the documents of that. Safety, the first one, safety is first coming first, and security after that, and also safeguards. This is something unique actually for our commissions. Why is that? Because different countries and states have been separated these obligations by different organizations. But here in the kingdom, we have all together. So safeguards, which is like related to nuclear materials, especially, is controlled actually and oversighted by the NRC. So this is something unique actually in our commissions, is to regulating nuclear and also radiation activity. Here I would like to show the pyramids for our legal documents within the country. Starting at the top, there is a pyramid. Start at the top of the pyramid, there is the national policy, which covers the atomic energy policy and also radioactive waste policy. Following by that, the laws that have been enacted and showed in the first slides. These actually both, to be approved, is going to the highest authority within the government of Saudi Arabia. This one already as a task have been done by approving and acting the laws and policy. Following that, the regulations, which is like a set of requirements for any licensee to be who submitting an applications or requesting and doing an activity of radiations have been to follow in order to give a license. And this one should be approved by the board of the NRC. Technical codes and standards. The last one is guidelines documents. Both of these two actually is approval of the NRC within the CO authority. Here are the list of conventions that we are as a SOTIO, like we have party of that conventions. And for an example, number 2 convention on notifications of nuclear incident, uh, we are should notify any party within that conventions if any accidents happening on that. And these have been addressed as a mandate of the NRC in order to detecting or there is a warning coming from any accident, we have to notify directly the party of that conventions. Let's take other examples. Convention on nuclear safety, which is like related to operating the nuclear power plants, safety from safety point of view. And also, as an example, is Joint Convention on Safety number 10, Joint Convention on the Safety of Spent Fuel and the Safety of the Radioactive Waste Management. There are some principles which for generating the waste and how it's going to be handled. This actually, the obligations, provisions for any states have been reflected within the law of nuclear energetical control. And also this all actually is published online. You can search for any treaties and convention, you can read it about it. Here we're moving to the second pillar of my presentation, which is the regulations. So I will give you a story about journey, how we develop the national regulations. Okay. We have joint cooperations with one of good and well experienced organizations as a regulator, the Finnish regulator STOK. We together developed the first draft for a set of regulations. After that, we're inviting the stakeholders, the international and national stakeholders. And I just like understanding some of our speakers have been participating in that, actually developing the second draft. The objective of the second draft actually is to modify the first draft according to the view and feedbacks coming from the stakeholders. The final steps actually in the local regulations or national regulations of the NRC is, as I said, approval from the board of NRC. This stage actually still we are working on that. So we are almost in stage number 2, not 3. 3 is going to be approved by the board of the NRC. And by the way, one of the times the IEA have been doing intermissions. Intermission is integrated nuclear infrastructures review. It's a services from the IEA to look over all the components in the country to see how the country is suitable to build a power plant, a nuclear power plants. They have seen it, our methodology actually to develop the regulations, which is like inviting, firstly, by inviting or cooperating with the well-established organization and then inviting stakeholders, national and internationally. They say this is an example, this can be classified as an example, as a good practice actually, because it have been built according to a strong and legitimate professions that have been reviewed by the mostly the who understanding the business well. Here are 15 examples of what we have been formed and be ready for the polls to be approved. Here you can see 15 regulations. The first one at the top left is radiation safety. And this is representing the GSR Part 3 from the IEA, if you are familiar with, which is like general requirements for radiation safety or protections. This is going to be like the first things for the polls to be approved. Now comes to the questions that we don't have, as a regulator, we don't have now a regulations, and it's under approval of the board. But what are we going right now assessing and approving the licensee? The answer was answered before in my presentations. The answer is we are going to use the IEA as a minimum requirements for giving a license, review the license or the applications. For in the current times, any users of radiation radiation fields wants to obtain a license, he should follow the IEA safety standards according to the decision from the Cabinet of Ministers who issued in January 2019. Right? So this is our main right now regulations that we are using right now. To give you what is the IAS safety standard, is similar to the pyramids that I have been showed as a local one. At the top, there is fundamentals or the laws or something. Behind that or under that, there is safety requirements and safety guides after that. On the similar manner, for the security series, there is like fundamental at the beginning recommendation was like equal to the requirements and also for our regulations and implementing guides, technical guides at the end. All right. So I finished with the two parts and left with the third part of my presentation, which is showing some of the activities that are now running in our NRC. As I said before, we are covering nuclear and radiations, and this is something unique on us. Starting with the nuclear applications, we have two main projects. Low power research reactor, and this topic will be covered during the webinar by Dr. Mishari Al-Qahtani, the CACS organizations. And also the first nuclear power plants in the kingdom. During the video, you have noticed that there is a SNEP, or like there is Saudi National Atomic Energy Programs. It's announcing that we are going, or we are planning actually to study to construct 2 units, 1 giga for each unit to generate electricity from that. It's in early stage actually. They still under now study the sites as a site characterizations for stability for building nuclear power plants. Here are the CAS and will be covered by Dr. Mishari. I would like to say from our side as a regulator is still, they already having the constructions license and the rest of commissioning and operation to commissioning is still undergoing. And this is as a national beneficial actually for us. From their side actually as a research and going educational training for CACs and also for the national base and also for us as a regulator to go over the process of regulating. Assessing the applications, review the applications, and also engaging with the licensing. The second project I said is like still under the study as a site characterization of stability for building the nuclear power plants. Our main job right now is to prepare ourselves inside the NRC for receiving any times, solely or laterally. The application for granting the site license. And also we have early engagement with the licensee for discussing that matter. Moving to the second part of our activity is radiological. This is give you a glimpse about how much spectrum that we have as a licensee. We have almost 32 licensee covered like from industrial 410 almost, and 200 almost for medical license, and almost 130 for services and transportation of radioactive materials. We have more than 1,000 radiological facility, over 4,000 X-ray units, 1,200 CT scanners, and also 250 angiography, mammography, 500, and also 15 radiotherapy facility within Linux, right? Linux. For industrial research, we have 121 industrial radiography facility, 3 major actually industrial irradiator facility, almost 200 nuclear gauge facility, and 15 well logging users. One actually of the topics that have been mandated in our law and charter is to control as well of natural occurring radioactive materials. The Kingdom of Saudi Arabia, one of the top countries actually that's used that get the fresh water from sea desalinations, and the resulting of generating that or producing that there is a norm. The norm coming like can be like concentrated within the pipes, as you say, and the filters. We are mandated to control that and find like the oversights and controlling of the natural or norm materials. Here are the topic of emergency. So in terms of in case of the accident of nuclear emergency, لا قدر الله, NRC playing a roles among other organizations, national organizations, to control or respond to that emergency. I'm going to show that some of the activity going on both for national parks and also for nuclear. For national, there is before establishing of NRC, there were a committee called Permanent National Committee for Nuclear Emergency Response. It consists of different organizations within the country. The main output or the main activity of that committee is to set up national plans. The plans should consist of the roles and mandates of each organizations, not only before as a preparedness, but only before, during, and after any emergency or nuclear accidents. Of course, the national plans should update it in frequent manner. There is like every 3 or 5 years, the committee like gathering together and updating their plans. Now coming to the NRC mandate is one of that, as I said, from conventions. I have like number 2, early notifications. To notify the other party, you have to set the systems to detecting any radiations activity or radiations and abnormal activity. So we have 140, and we are going to increasing that number of radiation monitoring systems, stations, is like have been scattering within the country of Saudi Arabia, as the picture, as the map says. The other system that we have to develop is decision support systems. This system actually, as the Kingdom of Saudi Arabia have been surrounded by different country that is operating in the moment, nuclear power plants. But what's happening if there is like, la qadar Allah as well, accidents happening or something like that. So we have developed systems to support our decisions in terms of evacuations, shelter or taking medicines, iodine tablets. So the system works as follows. Firstly, as an input, you have to specify what's happening inside the reactors as a power plants. Is it melted? Is it leak? Is it something? And then after that, evaluating how the plumes and the winds are moving, how the water are moving underground, as an input as well. So after that, a decision will come as a supporting. What is the right decision to take? Is it evacuation, as I said, or shelter? The last things I will presenting in my presentation is in order to control illicit trafficking happening in the country, we have constructing a gate that detecting any illicit trafficking for radioactive materials. And here you can see some of the pictures that's already installed in Riyadh airports to detecting actually the illicit trafficking for radioactive materials. And we are planning to increasing this number actually among other airports, international airports, and also for scrap yard, metal scrap yard, because we have like many of those scrap backyards, and we're planning actually to control that as well. This actually brings us to the end of my presentation. I hope I was like clear enough and informative information. Thank you. Thank you.
Yes, so we do have a question from an attendee.
Yes.
They would like to know, in your experience as a regulator, what is the first steps they should do after they've graduated as a medical physicist?
What is the first?
First steps they should be doing after they've graduated as a medical physicist, if you know.
All right. So if I understand the question as well, is that what is first step when you graduate from the medical physicist to do as a steps? All right. As a medical physicist, there are like a plenty actually of job, not only for the regulators. As a medical physician, I think you have a good understanding of how the radiation protection is affecting the body. Okay, and there are like several actually jobs and professionally, not only in the hospitals, but also in some of the regulators that's controlling the, for instance, health and safety environments department here needed medical physics. So what is encourage you actually to do actually is firstly to read the law of that. If you are involving in radiations in any kinds, just read the law to understand your rights as a medical physician and also what you have obliged to do for the society. Secondly, there is like a set of radiations requirements standards in the IA. You can check on that also. You can understand how the systems work in the IA, and also you can attending a free online courses in the IA and others organizations internationally. I hope I answered the questions as a guide.
Thank you.
Yes, please, Doctor. Use the mic, please.
Sorry. Many people are asking questions regarding the radiation safety officer renewal of the license, the exam, and more recently for the RSO courses. So what the stages actually?
Funny things that I coming here to this webinar and accepting that questions to be asked for the regulator, honestly speaking. But I'm not that listening coming from the speaker, but anyhow. Yes, the renewing of RSO right now is like right now is not a black, not a white things. It's a gray right now. But we have to say something that's right now we are developing not only how we are going to license the RSO, but the whole system, as I showed, the whole oversight is going on that. By the way, I'm responsible actually as a Dr. Muhammad Bahmed have been with me as a regulatory operations, but basically I'm an acting manager for national registry. One of the things we are right now, I'm trying to build is developing a system to register any radioactive materials within the country. Not only that, also the information of the facility. So if the facility should have a profiles of information within our premises, our data, to explaining what is inside it, how many RSO they have, how many cesium, for example, they have. The same information have been presented by Dr. Muhammad Bahmed will be in our system and will be understood how it's going to run. So we are still just, we are like early establishing organization. I believe you are expecting more than that, but we are pushing hard actually to make things right for everyone, for everyone.
Thank you, Muhammad, for your presentation. It was really insight and detailed. I have one question. I'm not sure if you could answer it, but this is many people are asking about radiation safety officer exam. So we couldn't find any information about the next exam and when it will be available. So if you have some information and you could share it with us, I appreciate it. Thanks.
All right, so it's similar to the questions for Dr. Albert actually is the RSO, how the exams will be. I will repeat the answer by Dr. Muhammad Ahmed. We are still working actually to set up a systems, not only for licensing only the RSO, but also for how to assist the qualification of the RSO, how the training have been, what is the training should be having. So one of the regulations will have the qualification of personnel. So the qualification of personnel is important for us that the right persons work in the right place. Still, the same answer will be is we are still building, developing the system for regulating and also for licensing the RSO. And I hope that sooner you will see something that's meeting your expectations actually on that.
Another question. So is it
دقيقة تفضل تفضل دكتور
Go ahead.
لا لا اسال questions بعدين ننتقل تفضل تفضل تفضل.
Okay, one of the problems that we're facing in KAUST is the long-lived radioactive waste. As you know, we generate waste from using tritium and carbon 14,
Yeah.
tritium H3 and carbon 14 in our lab. And this waste right now is stored in our radioactive waste storage.
Yeah.
But we are accumulating a lot of liquid waste and solid waste. And my question is that, is there any hope to see the national radioactive waste cemetery or graveyard soon?
All right, so to answer the questions, I would highly recommend to you actually to go to read one of the policy that I have shown is the national policy for controlling or radioactive waste management. This policy set a clear lines or headlines for each organization within the country how to organizing the radioactive waste management in the country. Shortly or summarize of that policy, we have three parts actually on that. We have the generator or the facility who will generate the radioactive waste, it's a matter of cost. And also we have the regulator which is like going to regulate the safety of transferring and also putting on a disposal of the radioactive waste. The third party is like the holder or let's say the operator of disposal facility. These organizations by name is the KCARE. By its mandate, which is established in 2010, they are mandating actually to operating the national policy. I would like to support the answer, which like having a national disposal facility as a facility is going right now in the country. But we just like approving the national policy, the legal documents for that. To take, so it will take times actually to make this the body to running or to activating the policy in order to see a national policy or to see the national center for disposal of radioactive waste. Okay.
Yes, as a,
So for the regulator.
yeah, we like you guys.
Okay.
So I have a question about because I'm interested in nuclear emergency or nuclear and radiological emergency. So how frequent do you guys do drills or training?
Yeah.
So,
Honestly speaking, like I don't have a clear answer on that's how frequently we do, but we are participating as an NRC. This is what I can say. We are participating within international drills. So the last one we was holding in Emirates, that's drills for emergency as a national, regional or international base. We have participated on that. But the drills for the local, as a facility locals,
yeah.
because emergency can be classified as a local emergency in terms of facility and as a national base and also international base. We still, I don't have actually any clarity about how many drills have been done on that.
Okay, thank you.
Dr. Mohammed, very quick question. You mentioned now the NRRC are using the IAEA regulations as the minimum requirements.
Yeah.
So does that mean that the NRRC will use this for the future, or they will build up their own or our own national regulations?
Yeah. So I will answer the questions, Dr. The answer is no. We are not use is yes and no. Let's say. Yeah, why is yes? Because our regulations that I have shown it what behind developed as a steps have been built according to the IAEA safety standards. So it's plus on the IAEA safety standard, but it's not minus. So the IAEA is the minimum requirement that you are using. No, the answer is, is like it will be affected as a minimum requirements until we enact or approving from the post the national regulations. So after approving the national, there is like a profession will be within the regulation. This will be affected as a requirements for everyone in the country on that date. So after that, you have to use the regulation of the NRC, not the requirements.
Once we have this, the national one, we will just leave the
Exactly.
IAEA. And that's how long that will take, maybe? Or?
Yeah, if there is, that's what I'm trying to say. If there is any updates or any international, because what we have understood from different nuclear accidents around the world, or different accidents around the world, every times the international arena understanding something more requirements to put it in that. So this is updating of the regulations is sitting on us. So the version 1, after that's going to be version 2 and version 3, and also you can follow after that. And it's an updating of what is happening in the international. So we are, as a regulator, we have to make sure our national or local requirements or regulations is based on the international. Any questions? Yeah.
Yeah, we have one more question from the audience. They would like to know what licenses or certifications are available for those that want to be certified as a radiation safety expert.
All right. So from the questions we are have been asking about how to renew actually. So again, the answer will be for right now at the moment. So we don't have like anything to say about what is the right qualifications or training you have to attend in order to get the license. But we are developing a systems. It's going to be online. This is something I can disclose. The online systems is allow you actually to see what is the requirements you need it as an individual to renew or issue a new license from the NRC. I hope I have enough more than that information, but still, we are developing and working with that. Yes. Yeah. The types of actually, so thank you, Dr. Nasser. The type of license here, the same, will be the same system. The old system of having a license as I saw in the medical, having a saw in the industrial, this is what's happening before, right? And also for the research license, so I'm not sure if it's going to be changed or be the same manners. So the system as a whole will be developed and will be disclosed soon. And we still, not only the website actually is ready, online website, but still the legal, how we can control the legal things. Okay. Right. Thank you very much.
Thanks, Engineer Mohammed Farhan, for your presentation. It was very nice and comprehensive. Now, our next speaker is Dr. Nasser Shubair. He's the chairman of the Diagnostic Radiology Department. He's the director of Medical Research Center and head of Radiation Protection Unit at Jazan University. Please welcome, Dr. Nasser.
Assalamu alaikum wa rahmatullah. So today I'm going to talk about radiation emergencies. So I'm very interested in this topic as I have worked on my PhD dissertation for a scenario in Riyadh. Let's first define what is radiation emergency. It's a non-routine situation where there is a release of radiation or risk of exposure. And let's see that clearly that it's an uncommon situation, and it's not expected to have many accidents involving radioactive materials, but the possibility is there. Why it's important to focus on radiation emergency? Because the profound and the tremendous damage to the economy and the environment, and also the significant burden, medical and physiological burdens. Radiation emergencies is general term let's just talk about how we define the radiological emergency or nuclear emergency. A small difference between them: nuclear emergency, it's the nuclear incidents that involve detonation of nuclear device like nuclear weapons, something with blast or detonation, explosion. Other than that, any accident or incidents produce radiation, but without detonation, we can categorize that as a radiological emergency. In terms of magnitude of radiation emergencies, we have small scale emergencies and we have large scale emergencies. The small scale involving small amount of radioactive materials, the potential exposure or contamination could be one or few individuals. It could happen in laboratories, hospital, a small incidents in nuclear power plants. On the other side, large scale emergencies, when it's involving large quantities of radioactive materials, and also the exposure could be for a large group of people. And it could happen as terrorist attack involving radiological weapons, nuclear weapons detonation, and also large scale nuclear power plant disaster. The possible consequences of large scale event with radioactive materials involving psychological and medical and radiological effects on individuals and their families. And we said that it's uncommon, but when we have, when you guys remember Fukushima or Chernobyl, we have seen what's happened. So it's really a disaster with the full meaning of the word. So also disruption of local economies and the food chain. Also disruption of local and national transport. Disruption of global capital markets. Long-term health and economic effects. And for the long-term health, we saw like after Chernobyl, 30 years after Chernobyl, and still the health damage, health effect is still going. The International Atomic Energy Agency have a scale for nuclear and radiological event scale. They have a category of, for the accident from 0 to 7. For example, for 7, like Fukushima and Chernobyl, it's on the number 7. Let's have a look on some of the statistics for the radiation accidents. So between 1944 and 2009, we have about 500 accidents, about 3,000 exposed individuals, and with fatalities around 140, 130 from them related to exposure to radiation. Also, we can see that most of the accidents, it's in the industrial field. So, and maybe the reason behind that, at that time, like now the situation is better, but at that time in the industrial field, sometimes the hire or recruit low skill radiation professional, or maybe they are not in the field of radiation, so they have no experience about radiation. So the possible exposure pathways and consequences. So we have the internal contamination, as when the radioactive materials find their way inside the body through inhalation or ingestion or absorption through the skin or wounds. External exposure and external contamination when the radioactive materials cover the cloth or the skin. Now let's talk about the type of nuclear and radiological emergencies. So first we have, I'm going to go over them in just without any further categorization, but we have like the first 4 of the types, it's related to malicious acts or terrorism event. So one of them is a radiological exposure device. It's usually a stolen radioactive source from in like factories or from hospital. Commonly used radionuclides are iridium, cesium, cobalt, strontium. People could be exposed to radiation, like a lethal dose of radiation. And these accidents, when someone like steal these sources and plant them in public place, like what happened, I don't remember any accident related. Okay, so anyways, the second type is dirty bomb, and this is a real issue, and we have seen like many governments, they are taking this matter seriously. Like in the United States, they have drills like every 2 years by FEMA. So for the dirty bomb, it's a mix of explosives such as dynamite with radioactive powders or bullets. It's not involving any like blast like nuclear power and nuclear weapons, but the goal to spread contamination over the areas. Two incidents or two examples for the dirty bombs. It's in Chechen in 1995 when a group of terrorism, they planted cesium and explosive devices in playground, but thankfully it's not detonated. So, but the fear and the psychological impact is still there. So when the public knew about the situation, it was terrifying to them. The second situation 3 years later, when also Chechen Security Service renders also plant dirty bomb in a railway line, and also it was not detonated and it was recovered. But still, when we talk about radiation or nuclear accident, we're talking about psychological impact. It's the most serious thing, because one of the goal of terrorism or terrorists is just to plant the fear in the public. So even the accident is not happening, but still the plant the fear in the public. So another type is improvised nuclear device, which is let's say it's a small nuclear weapon. It could be fit in possible in a suitcase with a yield between 10 to 20 tons. This one is made by the Soviet Union to target the NATO, but it wasn't used. So other type of nuclear emergency is nuclear weapons. We have seen in Hiroshima, where almost 90% of the city was destroyed, and within a second, more than 80,000 people dead. So when we talk about nuclear weapons, we talk about mass destruction. In a few seconds, in less than a second, a tremendous power will be released with thermal energy, radiation, and also blast. Nuclear power plant. So it's another kind of radiation emergency. It can cause contamination over a wide areas. Very significant nuclear power plant radiation emergency. What happened in Philadelphia, the 3 Mile Island, back in '79, and also Chernobyl, and the last, it's Fukushima, 2011, and they're still working on the recovery. Transportation accident. So if we look at how many yearly the transportation of radioactive material, it's about 3 million packages per year transported between countries, between agencies, or between two entities inside one country or internationally. So, but due to the restriction or the good regulations, not many the transportation accident occurs. So let's just mention one example here. What happened in Mexico, where a truck transporting a large amount of activity of cobalt teletherapy source from Tijuana Hospital to a waste storage facility. So this triggered a national-wide search by Mexican authorities, and the truck was recovered a day later. It was discovered that the source had been removed from its shielding, and if you see in this picture, you'll see it's like it's a waste in an industrial package, and they remove it from the package. The source was found shortly after in nearby field, where it was safely recovered, and the thieves that stole the truck could be exposed to a lethal dose. And I went back to the newspaper in 2013. It happened in 2013. So the first thing the media is talking about, they said radioactive source that was stolen and could be used as a bomb, radioactive dirty bomb. So this is something terrifying. Like governments, they work hard not to prevent all this situation, even small accidents like in transportation. So in occupational accident, we know that radiation sources widely used in hospital, research centers, and also in the industry. And while Mohammed Farhan was presenting his presentation, I saw that we have in Saudi Arabia like around 400 something industrial what factories or yes, they are licensed, and which is good. And we also saw from these statistics that the most accidents are from it's from industrial in the industrial field more than the medical field. And this is usually happened. Why? Because whether radiation sources are stored or used incorrectly, or safety controls malfunctions, or safety procedures are not followed. This is basically the three main reasons for these occupational accidents. And look, let's have a look on some of the examples for occupational accidents in the medical field. We have the miscalibrated radiotherapy devices, which is very common, around like 5 or 6 accidents occurred around the world. And one of the examples in Columbus, Ohio, between 74 and 76, where 10 fatalities and 78 injuries. In Panama City, in Panama, within 1 year, more than 17 deaths and 11 injuries. And the reason behind that, miscalibration for a radiotherapy device. And we have the guy for the calibration, Dr. Mohanna Areb. So we are safe here in Saudi Arabia, inshallah. But he's busy with his presentation. Anyways, in the industrial field, we have plenty of examples. The one that I like, and also in my lectures, I always present is what happened in Peru, where one of the workers picked the radioactive source and put it in his pocket, and for 6 hours he was having the source in his pocket. He returned home, sitting around his wife and son. Then he complained about he have like some pain in his back, and then he went to the doctor. The doctor said it could be some what? It's not maybe some stick, yeah. So I forgot the English word for that. So, anyways, and then after a couple of days, he started developing symptoms and developing skin problems, and then the situation was worse with the time where they couldn't treat him in Peru. They transfer him to France, and then he spent there many months for treatment. And at the end, the situation was really, really bad. They amputed his leg, and thankfully he survived, but it was very large exposure to the worker. So to prevent and mitigate radiation emergency, one important thing to have it registration and control of all radiation sources during all phases: commissioning, application, transport, and disposal. And I think most of the countries now, they have very good regulations and restrict control around the radioactive sources. Also promoting or the safety culture. And this is why we are here today. And I thank KAUST and thank Muhammad and Eric and all the guys here in KAUST. One of the goals we are here today, we are talking just to advance or to promote the safety culture. Also to prevent and mitigate a radiation emergency, regular training should be done. And as I remember, I spent some time in the United States, like 8 years, and I worked on emergency. I know FEMA, they have 2 years training programs. Like every 2 years, they have to have drills, which is good because you have experts, you have new staff, you have to update some of the information. So regular training is really important. And finally, the planning and preparedness of overall response. This is really important because during the accident or the emergency, there's no time for planning. There's no time to think about, so you have to act. So planning in advance is really important. With that, I finish my presentation, and I really thank everyone for listening to this presentation, and I thank KAUST for giving us the platform to talk here. So, am I in time? Yes.
So we have a question from one of the attendees. Is there a way to avoid the consequences of nuclear disasters?
Is there
What are the ways to avoid any nuclear disasters in general?
Okay, so first, the NRRC, so they have to do their work or do the job perfectly, so they have the full control on radioactive source inside the country. So on the other side, for nuclear emergency, I think it's a global. The international community should work together to prevent any use of nuclear weapons. And I think there is a good work on international level for that. Yeah. So also, the workers should do their part by having trainings and having continuing education. This will improve the performance level and the safety culture.
Thank you.
Yes. Thank you, everyone.
Thanks, Dr. Nasser, for your informative presentation. I think the answer to not to prevent nuclear disaster, not to use any radiation. But this is will be impossible. Anyway, our next speaker will talk about radioactive waste. And radioactive waste is actually one of the worst nightmare for nuclear industry. And people and the world is still looking for a permanent solution to this problem. And I believe anyone who discover a solution, he will be awarded with Nobel Prize. Please welcome with me Dr. Yazid Al-Ashban. He's the assistant professor and head of the medical education unit at King Saud University. Please, Doctor.
Thank you so much, Thank you, Mr. Muhammad. Thank you, Mr. Eric. Thanks, Kaust, for the invitation. Today, we will briefly speak about the radioactive waste management. As all of you know that all practice that use nuclear materials will eventually produce radioactive waste. The nature of this waste will vary from one radioactive waste to another in terms of volume, physical, chemical properties, and the concentration of radioactivity. So the radioactivity contained in the waste is hazard not only to human but also to the environment, to animals, to plants. So there are two common radioactive sources that mainly used in medical field and for research purposes. We have sealed radioactive source that can be used in diagnostic radiology. We can use these for example, in bone density, where they mainly use iodine 125, americium 241. They also can use for radiotherapy using iodine 125. Also, it can be used in blood irradiation. For the unsealed source, we have multiple types of radiation sources that can be used as tracer for calibration. They can use for research, for example, using DNA sequencing by using carbon-14, for example. So what are the main principles of radioactive waste management? First is to protect human health. Second is the protection of environment through the release or disposal of the waste material that should be minimized. First, we have to prevent the waste. If there is no way to prevent the waste, then we have to minimize the waste as much as we can. We have to do an assessment on the impact of the waste for human and also for protection of future generation. We always need to minimize the undue burdens of the waste on our new generation by spending on new technology, on research, and on training. So the main sources for radioactive waste, we can use it from the nuclear fuel recycle, where they use uranium, for example, uranium extraction, uranium enrichment, industrial application, for medical applications, for both diagnostic and therapeutic applications, for research and development, such as in the research industry, for the phosphate industry, for metal productions. So what will happen if there is no classification system for the waste? So the problem is the low and high activity waste will get mixed. So this is the main problem. Therefore, there will be a poor basis on decision of treatment, packaging, storing, and dealing with the radioactive waste. Poor segregation, mainly by mixing high-level and short-level waste, high-lived radioactive waste and short-lived radioactive waste. It will be a difficulty to structure a comprehensive radiation protection program dealing with the produced waste from the radioactive material. There will be a weak basis at the end of the waste management strategy, and will be difficulty to measure the performance of the radiation protection system. So therefore, we have 6 main classes of the radioactive starting from high-level waste, where it generates the most of the heat compared to the other kind or other type of waste. Starting with the exemption level, so these levels are related to the radionuclide concentration in terms of becquerel per gram. We have some selected radionuclides with this level, so any radionuclides below this level should be considered as exempt waste. We have, on the other hand, clearance level. So this is a term that describes the removal of radioactive material from the regularity control. The clearance level should not exceed the exemption level for this kind of waste. So what about the waste storage? So storage means storing or keeping conditioned radioactive waste in a good place, safe place, a place that should be monitored 24/7 with the logbook of the inventory, with intention to get it back after a small or large period of time, either for final disposal, for recycling, or for reusing it. So the final step of the radioactive waste, which is the final part, is to dispose the waste. So considering only when there is no intention for any recycling or reusing of the waste. This mainly include three main principles. First one is delay and delay. Delay and delay means that we have to keep the radioactive waste for 10 half-lives. So at the end of the time, the final activity will be lower than 0.1% of the initial activity. So this is delay and delay. We have dilute and disperse, and we have concentrate and contain to help us for fuel or for waste waste management. So radioactive waste disposal site should be selected to ensure that it's a good place based on different criteria, and should be safe to the member of the public, and also should be safe for our environment. So we have two main types of disposal method. We have the near surface disposal, and we have the deep surface disposal. So the near surface disposal is mainly for waste containing a short to medium half-life radionuclides, and should be conditioned first. If we need to place a long-lived radioactive materials or radioactive waste in the near surface disposal facility, it should be within a very small amount. The other option is the deep geological or deep surface disposal facility. It's the best option for radioactive waste disposal. It can contain long-lived radioactive nuclides with high amount of activity. So this is the best option for dealing with this kind of radioactive waste. We have another option that was that's deep ocean. So it's selected due to its high degree of dilution and isolation. This is not practiced after the 1972 London Convention. So it was practiced by several nations, but nowadays it's banned. So not permitted for high activity radioactive waste at the beginning. So for the waste volume management, as I said before, we have to prevent the waste. So when designing experiment or planning, such as in medical field, the using radioactive material should be based on benefit versus risk. So you should always use it as long as the benefit of the procedure is higher than the risk produced from this procedure. And you should only use the minimum required amount of radioactive material in order to minimize the radioactive waste produced. If we couldn't prevent it, so we have to minimize it. So the objective is to reduce the waste and the volume. Therefore, we will have to reduce the volume of storage, the treatment, and the final disposal, since it has consequences not only to the human, but also to the animal and plants and to the overall environment of the nation. Segregation, it's convenient to segregate waste in different categories based on the half-life of all of these wastes. So starting by 4 main types of segregations. We have waste with half-life about 10 hours or less, half-life of less than 10 days, less than 100 days, and greater than 100 days as a segregation, not mixing not mixing short half-lived radionuclides with long half-lived radionuclides in order to control, to manage, to reprocess the waste. We need appropriate packaging and labeling for the radioactive waste. And this correct, such as packaging, is essential components of the waste management system for biomedical radioactive waste. So the choice is necessary to minimize the waste of volume. So we don't need to mix high with intermediate with low radioactive waste. So as you can see, many of the places, they have their own site storage for just maybe for a delay or before pre-treatment or treatment, or before sending the waste to the vendor for reprocessing or for the final disposal. So in case that we need to transport the waste, transportation, the waste will be from the center or from the facility to the central facility for treatment, or can be transported for final disposal, or can be returned to the vendor for reprocessing, such as in spent fuel, if you are talking about nuclear reactors. So there are 9 classes of dangerous good, and no one of them is more dangerous than the other. So you can see class 7 is the radioactive waste materials. Around the world, you can see that there are millions of dangerous goods transferred between countries. And only just 1 million of these are radioactive materials. For shipping, this table shows the labeling of the radioactive waste in terms of something called transport index. So transport index is a term that gives an indication of the equivalent dose rates at 1 meter from the surface of the package. So depending on the transport index, we have different labeling of the waste. Finally, we have the treatment of the radioactive waste. So the ultimate goal of treatment is to minimize the volume of the radioactive waste. So usually a limited amount of treatment will be practiced at healthcare, for example. There are several processes used in treatment. One is mechanical, such as compressing, shredding of the waste in order to minimize the volume of radioactive materials. We have thermal, and we have also a chemical way to treat the radioactive waste. So finally, the optimum game here is to prevent waste. Okay, if there is a need for use radioactive material, if the benefits more than risk, so we use the minimum amount of radioactive material that will produce the minimum amount of radioactive waste. Then we have to reuse it again and again and again, okay, until there's no more useful. So then we have to recycle it. After recycling, the worst option will be disposal of the radioactive waste, since most of the long-lived radionuclide, as defined by the International Atomic Energy Agency, is the nuclides with half-life more than 30 years. So it will stay in the environment. It may affect the animals around the place, maybe will be transported to the plants and will eventually affect the human. Thank you so much, and have a good day. Yes.
So we have, excuse me, we have two questions. One is, do you have an approximation of how many radioactive disposal sites are in Saudi Arabia?
In Saudi Arabia, maybe Engineer Mohammed, he has a, yeah, they have a logbook for that.
Right, so firstly, I'd like to ask you to repeat the question, please.
Yes, do you know how many radioactive waste disposal sites are in Saudi Arabia?
As a final disposal sites, or like, let's say the final ones, until the moment there is none. Okay, but as an interim disposal facility, we have many actually, many facility right now. As Kaus said, there is some of the facility like for desalination water actually will reduce the norms. They have like within the facility an interim storage actually. They handle it and there is control by the NRC on the interim storage. So as a natural base, there is still one of the sites have been actually suitable for building a center for disposal as a final disposal facility, but it's still under development to establish and constructing a final disposal facility for radioactive.
What about the disposal facility that in Riyadh, Dammam Road? I think there was one disposal facility there, but I don't know if it's still working or not.
As I said, this is the one I referred to actually. Is not as facility as it is that is processing the radioactive waste in order to put it as a final positions as a radioactive waste. No, it's only locations that suitable.
Okay.
Have been studied as a site characterization to build a center, national center. That's and who are actually managing that facility is KACARE, King Abdullah City for Atomic and Renewable Energy.
We have one at
Not
King
us.
Saud University that just for delay. Yeah. So they keep the radioactive waste for a small period of time, usually 10 half-lives for small, for short-lived
In terms storage actually
Yeah.
for it says in terms we call it as a regulator in terms storage of radioactive waste management.
Yeah, they mainly use it for the waste from nuclear medicine and radiotherapy at King Khalid University Hospital. Yeah. So, but a final disposal,
Still.
I don't know. Yeah.
Still we
no.
develop it actually in the country as a final disposal, yes. And KACARE taking responsible for that.
Yes, thank you. So just a quick question, Dr. Yazid, Engineer Muhammad, he talked about the site. What is, I know you have experience on radioactive or near surface disposal facilities. So what is the parameters of the condition that fit a good disposal site?
Yeah, this depends on, let's say, if it's for a nuclear reactor. So this will depend on the type of the reactor itself. So I did my my dissertation on the waste management for a near surface disposal for both near surface disposal facilities and deep disposal facility for a hypothetical nuclear power plant in Saudi Arabia. That was they did a contract with the they was planning to build a SMART, which is the Korean reactor. And we did some research on that for proposing the site and proposing the best options for dealing with the waste that will be produced from this type of reactor. So it's mainly, it will depend on the type of reactor. So each reactor will produce, sometimes they have common waste, but still depends on the type of reactor. Okay, thank you so much, guys.
Thanks, Dr. Yazid, for your presentation. And now our next presenter is Dr. Abdul Qadir Al-Aidarous. He's a professor at the physics department in King Abdulaziz University. Also, he's a radiation safety expert. And he's the head of Photon Center for Radiation Consultancy. And he will talk about the non-medical human imaging, justification, ethics, and regulations. Please welcome.
Okay, thank you. Bismillah ar-Rahman ar-Rahim. My presentation was on the desktop, or I have a. Oh, sorry. Okay, Bismillah ar-Rahman ar-Rahim. Thanks. First of all, we'd like to thank KAUST for this kind invitation and hospitality, and for initiating this first meeting on radiation protection and safety, which I think the first of its kind in the kingdom. The topic, as we can see, non-medical human imaging, which I give it abbreviation NMHI, justification, ethics, and regulations. Okay, well, let's first define what the non-medical human imaging, and then I will say what I'm going to focus on. From the name, I think it's clear that we are talking about something non-medical, but we are using the medical equipment sometimes. So it's a non-medical human. This is defined by the European Commission that any deliberate exposure mean will be something planned exposure of humans for imaging purposes, where the primary motivation for making that exposure is not related to health. That is the main thing, is not related to health and well-being of the individual being exposed. Okay, so what is the new about this kind of practice? So it is not medical, it is not related to industry, it is not related to any power generation. So this is some kind of practice that the regulatory bodies and the governments are concerned about. The IEA in safety or general safety guide number 5, they said explicitly decisions on their justification are left to the national government or regulatory body. Well, my talk actually split in 2 parts. One is about that part, the justification, and where these justifications lie in the radiological protection system. And then I will move on to the non-medical human imaging. When I started just preparing this or picking up the title or the topic for this webinar, I just realized that we'll have, I think, a number of audiences, probably more than 300, I believe, from different from different sectors. So what kind of information, knowledge about radiation protection that I think, from my experience that I've been in radiation physics, radiation protection for maybe since 2000, and there's some gaps or misunderstanding, sometimes underestimating some part of the radiation protection system. What is it? It's lie under the justification. So let's start with the definition or the objective of our, well, let's start with this phrase. This phrase saying, radiation protection is not mainly a matter for science.
So if it is not matter for science, so who other people that this radiation protection would be matter for them? This saying actually comes from one of the pioneer. His name is Lawson Taylor, he died in 2004, and who co-founder of ICRP. What he said in one of his remarkable speech, radiation protection considerations go well beyond science into philosophical, sociological, political, economic, and moral areas. So we are not only talking about science when we talk about radiation protection. I know the science is very important. Our regulations are based many on the science evidence, but it's not only about science. So what he said there are three parts that constitute our regulations, our system of radiological protection. And these are science, which we are all talk about in our programs, our education. But there's some other parts which sometimes are missing and misunderstood, or as I said, overlooked, which is the ethics and the societal values, which I'm going to go through it just in a minute. And the experience. So experience, science, and ethical all together has to combine and constitute our regulations. Okay. Sometimes we ignore the ethics and sometimes the experience and okay, I'm doing the right thing. No, we are missing some of the pillar of radiation protection. So what these pillars, you will come to it. So what is radiation protection? What is the objective of radiation protection? Why we are here? What the radiation protection specialists are doing? Actually, I would summarize it in this very short sentence. Radiation protection regulations are designed to prevent deterministic effects and minimize the probability of stochastic effects. Prevention, so those who are not familiar with the deterministic and the stochastic deterministics, it's something that has a threshold, has a dose. Once you exceed that dose, so there will be kind of effects, biological effects that can be shown, that occurs normally at high doses. So alhamdulillah, the radiological protection system is preventing that such kind of deterministic effects will occur. But we don't say preventing the stochastic effects. We are saying minimizing. There's no way to prevent the stochastic effects. The stochastic effects, by the way, mainly it's cancer and genetic effects. Why we cannot prevent the stochastic effects? Because the ICRP are relying on the model of LNT, linear no-threshold model. What they said very strong statement and very hard fact, which is, I think, this one. What they said, harm can occur at any dose level or any level of dose. That means the probability of developing cancer can occur whatever the dose that you have, the probability of cancer is there. There is no threshold after which the cancer will occur. That is a very hard fact. Unfortunately, this is what ICRP actually adopting and following. If there is a threshold for the stochastic effect, I think things will be much, much easier. So I'm just have the speed meters just to present and see people, I think they will understand when they say the speed meter. So I mean, if you're driving maybe even 5 kilometers or 1 kilometer per hour, there's a probability of risk. Even if, as you increase the speed, the probability of developing cancer will also increase. Not only this, what they said also, very small exposure when you sum it, it equals to single one exposure, one single large exposure, okay? These both, or they both cause the same stochastic health effects. Can you imagine? So it's either you divide it into small parts or you have it in one shot, it's the same probability of effects. So the conclusion of this, persons must be protected from ionizing radiation at all those levels. There is no single, okay, so we'll see what we are actually paying the price for this kind of conclusion, because this is the system of the international or ICRP or the IAA or the system of radiation protection. Oh, sorry, I'm having the sound is go because now no, for you, maybe for the audience behind the screen. No. Okay, okay, because now I had this. Okay. So that is very, very hard facts, and all the radiation protection system are based on these facts. Okay, since someone will also this in a minute, but okay. These three general principles of radiation protection, Engineer Mohammed just mentioned very quickly, which is, I call them the pillar of radiation protection system. What they are, or what are they? The first one is the justification. You are not allowed to use or practice or adopt any ionizing radiation unless it produces a sufficient benefit to the exposed individual or society to offset the radiation harm that it may cause. You have to have a proper justification in order to do so. And I just give it a red line, so a red light. So you cannot cross, you cannot go ahead until you present a justification, which is a procedure that we have to follow, which is not something easy. The problem about justification is what? It's not something easy. It's a subjective concept. It's not something science-based. Because it's a subjective concept, we need an ethical decision-making. So what I consider to be right, some other people will say, no, this is a risk for me, but it's beneficial for me. So it has to be like a debate or negotiation or convincing between the two parties. Once you have the justification, you prove it, you go to the next step with the optimization. The optimization, okay, now you are allowed, fine, you go, but before you go, you have to really show me that you actually have the magnitude of dose received, the magnitude of dose received, the number of people exposed, and the likelihood of unnecessary exposures are kept as low as reasonably achievable. The problem that we face, and I think NRRC, they know this, people saying, okay, why I am using a radiation equipment with very low dose, a minimum dose, and sometimes within the background, already within the background, why I'm not allowed to use it? Say, okay, no, you have to have justification. So it's very important to know. The third one is the application of those limits, which is now you have the right, but please show the speed limit. Now, this is another one to show the importance of justification. This graph is, you see, it's 1987. The dose per individual was 3.6 millisievert per year and constitute only 3 millisieverts from the natural background and 0.7 from mankind or from man-made, radiation, which is basically medical radiation. After 20 years, what's happened? That number increased up twice. So now instead of 3.6, now becomes 6.2 millisievert per year. And the radiation, the natural, as you see, does not actually change very much. What it changed is the medical exposure. The medical exposure becomes almost 3 times or 4 times more. The question, why is it more? The study, the research showed in the United States that third of this dose, 3 millisieverts, actually is unjustified. So there's many practices in the medical hospitals are unjustified. So the justification is sometimes ignored for some reason. The non-medical human exposure, there's 2 categories. One, the first category, we call the medical equipment, that the exposure is done in a medical radiation facility and is run and assisted by radiologists or radiological or medical personnel. The second one is the exposure is done in a non-medical facility, and the image that we are getting are assessed by the non-medical staff. And each one has a different procedures. And there's an example here we see now in a minute. The security screening of passengers is from the second category. There's two types: backscattered radiation, X-ray and transmission X-ray, and electromagnetic waves. You see the backscatters produce less dose than the transmission X-ray images. So there's for the smuggling body, sorry. And for this is for the backscatter, this one, with the guy with the gun. Okay. So that's there's justification assessment that we have to go through it. Unfortunately, because of the time limit, we will not be able to say everything. Security screening for vehicles is another part and important issue for non-medical imaging. It's really important. It's nice. I mean, it's good to have such a system, but be careful. You have to go through a certain procedure to justify your work. Are you going to scan all people that are going through that gate? No. So how many people are going to? Sometimes maybe all of us can be scanned and we are not really doing any harm to the country or to the customs, whatever. Okay, that's those determination scenario for flights. You can see that the number can go up to 0.4 millisieverts, 0.6 millisieverts, which exceeds the 0.25 millisievert established for this kind of practices. Justification process. This is a tedious work, a long way to go. It's not something that we can do it in one meeting. So we have to gather all the information, input data, surveys, experience. First of all, define the need. What is your threat? The probability that threat will occur. Once you define your need, then you go to the evaluation. So what kind of equipments, devices, techniques that you need to have in order to solve your problem? So you have to show that kind of evaluation and to evaluate that technique that you want to. Is it ionizing or non-ionizing? Has any environmental impact or not? And then we go to the third step, which is the evaluation and privacy concerns. Lastly, we have the benefit risk analysis, which is also very, very important, but it has to go this way, not the other way around. Okay, this is a weighing risk benefit. One thing just to see here, I want to say that for medical, the patient are exposed to radiation, fine, but he's at risk, but at the same time, he is benefiting from the radiation. Whereas for non-medical imaging, so the person is actually exposed to radiation and he's at risk, but he is not benefiting from that radiation. So we have to provide some justification. If I am, for example, working with the customs or the airport, I have to say something about this. Okay. In MIH, it's going to be used. I believe that for the vision of 2030, we may expect more people coming to the country, tourists, investors, pilgrims, customs. So customs and borders, airports, maybe building more railways, drugs and weapons inspection, pre-employment health assessment, sports. So all these sometimes we may need to make some inspection for them. Conclusion remarks. That's the final slides. Okay, radiological protection system, guys, is designed not to restrain you from using radiation techniques. That's the message that we want to deliver to the audience. We are here to help you and encourage you to use radiation techniques. However, we want to use them safely and efficiently. Justification comes before optimization, not the other way around. Periodic justification must be, or assessment is required. It's not only one step or one dime. So from time to time, you have to go through it. Decision making is based on ethical requirements and experience, not on science. That is the hard, the difficult part of this bill. Even, and this is something that people actually ignore it. Even when the doses will be below the public dose limit, justification and optimization must be implemented. Don't say that I have a low dose. No way. No need for justification. I mean, people are safe. The radiological protection system doesn't work like this. It works at first one, justification, second one, optimization, third one is implementing of the dose limits. Lastly, radiation protection specialists need to develop skill such as analytical thinking, critical thinking, reasoning, problem solving, and risk analysis. These things, actually, some kind of skills, we ignore it sometimes. We teach our students. I think the program itself, sometimes we omit such kind of important skills in this one. Lastly, in a nutshell, and summarize the whole presentation, that we have justification with the curvature road. It's not something straight that we can go. A lot of factors that we have in our way to reach and to apply them. When we get the license, or get at least authorized, or we have the good justification, we can move on to the ALARA and those limits, that which is a science-based, most of it, and we can go through it. But don't go do your practice, and sometimes in the hospital, for example, people actually, okay, I'm exposing someone to radiation at CT, for example, and they say, okay, we should not be exposed this patient. Said the dose, he said, the dose is very low. But you are actually you are violating the rules, because you're exposing a patient that he doesn't need to be exposed. There's no good justification for this, even if you are actually following the ALARA principle. That is one of the important principle of this. In educational system, education programs, most of the conferences, meetings, programs, whether we attend, we are actually sitting in this area. We are focusing on this area. We rarely go to this area. I know it's not only the governmental regulatory work, but also as a radiation protection specialist, that we have to take into consideration this one, because this might also contribute to the reduction of dose to the public. Thank you very much.
Nice lunch, as we did. And our next speaker is Dr. Musaad Al-Malki. Before I introduce him, I'd like to mention that we have only 2 presentations left in this webinar. Our third or final presenter from Aramco couldn't make it to the webinar, so we're gonna finish earlier today. Also, we will try to answer most of your question. However, some of the question requires detailed answer, so we're gonna send you the answer in your email, or it will be posted later. Dr. Musaad Al-Malki, consultant and radiation protection expert. He is General Director of Radiation Protection Program at the Ministry of Health. He's also Assistant Deputy Minister for Preventive Health at Ministry of Health. He was going to talk about the radiation safety program at the Ministry of Health. So please, Saad, if you are ready, we will run your presentation from here. So just let me know and I will change the slide for you. Thank you. Dr. Musaad, can you hear me?
ايوه اسمعك. بسم الله الرحمن الرحيم. First, I would like. Do you hear me, Doctor? Is it clear? Hello.
Yes, it sounds
okay.
Clear. Yes.
Okay. Thanks for inviting me to this event. And today we are going to talk about the radiation protection at the Ministry of Health. Okay. So it does not move. Why? Second slide. Okay. So we'll move it from. Okay. So 35 years ago, after Chernobyl, radiation protection department had been established as the assistant deputy for preventive health to protect the medical imaging staff and patient, also public, from the health risk attributed to exposure to ionizing radiation at the Ministry of Health. Why it is not move? Okay. So the duty and responsibility of this program, it represents the communication link between the Ministry of Health.
Dr. Musaad?
Yes.
Dr. Musaad, can you turn on your camera? Your camera is off right now.
Yes, I prefer to be off. Is it okay?
Okay.
Okay.
Yeah, it's okay. That's fine. No problem.
Okay. Okay, so back to the duty and the responsibility. It represents the communication link between the Ministry of Health facility and concerned local national institution like CAST and RRC, Saudi FDA, and Ministry of Interior regarding any activity on a field of radiation. Also monitoring the communication commitment of all Ministry of Health facility to the rules, regulation, and instruction regarding of ionizing radiation protection laws and system. Also issuing radiological protection rules, regulation, standards, and instruction for controlling exposure at health facility. Also for responsibility centering monitoring for radiation dose to all Ministry of Health staff using TLD in their workplace. The second slice, you see it is monitoring the use of radioactive material arriving to the nuclear medicine department and other department, for example, laboratory, assuring the national limits are applied to the radiation exposure, different radiation dose, contamination of radioactive material, and the limit concentration there is radioactive material in health facility. Also evaluating the revising and approval of structure planning for diagnostic and therapeutic radiology and nuclear medicine in terms of radiation protection requirement. Issuing and practicing license for diagnostic and therapeutic radiology department and nuclear medicine department. Next slide. Next slide. Central monitoring to equipment and material of radioactive source at the health facility in the term of the import, export, and transport, in additional to improving the method and the procedure for obtaining the radioactive source. The inspection of Ministry of Health facility in terms of radiation practice, staff, ionizing radiation source, and workplace that are affected by this source. Monitoring the application of radiation protection guideline in the medical field and checking the implementation of all protection and safety requirements, which include human resource, organizing, technical, and administrative requirement. Also revising the protection and safety periodic report of ionizing radiation from licensed health facility to ensure that it comply with the application rules and regulations. Okay, other responsibility, revising the accreditation of radiation emergency that are provided via licensed health facilities to face a nuclear and radiation accident that may happen inside and outside the facility taken in the concern other institution requirement, implementing radiation survey, radiation measurement, monitoring radiation pollution with the component and approximate measure of nuclear and radiation accident. Also assistant of the specialized in the Ministry of Health department by performing the ministry national plan for facing nuclear and radiation emergency response. Spreading scientific awareness among health facility staff regarding safety and radiation protection from ionizing radiation. So next slide. Okay, here we have a department in this program. We will move the second, please. Here we are accredited from NRRC to provide 5 services. The first one, it is the TLD readers and survey meters, training and QC, also wipe test examination. Okay, next please. So here the first department is personal dosimetry. It serves the radiology staff at the Ministry of Health facility where they given TLD to measure the amount of radiation exposed to their body tissue during their work. We can see here in the slides, it show we started 86 with one TLD reader here, as you can see, one TLD reader, and we cover 1,000 practitioner health in the radiation field. And in 2020, we have 7 readers, as you can see it here, and cover more than 30,000 workers in this field. Okay. The second department is the radiological survey. This department is in charge of an inspection, which is used to know to what extent the radiology department are committed to rules and regulations of ionizing radiation, aiming for early detection of excessive radiation exposure, either due to the radiation leakage or as a result of unshielded radiology rooms. And here in this diagram, next please. This diagram here, we started in 86 with 4 survey meter, with 4 survey meters, and we surveyed 20 X-ray rooms. In 2020, we surveyed more than 1,400 rooms by using 227 survey meters. Okay, next please. The third, license and monitoring of radioactive material usage. This department is in charge of monitoring the nuclear medicine department and hormones labs, which gives indication to what extent their commitment of ionizing radiation protection rules and regulation, and the early detection of excessive radiation exposure due to contamination, and recording their information provided from hospital that use radioactive materials. And we can see here, we start in 97. We have been accredited 10 nuclear medicine department from NRC at that time, and 2 radiation safety officer. And 2020, we had been accredited 23 nuclear medicine and 30 radiology department, and more than 100 radiation safety officer. Also, we have certified 177 private hospital from the Ministry of Health. Okay. Radiation instrument calibration and safety department is responsible for monitoring all calibration, maintenance, and repair required to all requirement of radiation protection department, equipment, survey meters, TLD readers, and laboratory equipment. So we have now more than 300 equipment under maintenance contract. Okay, next please. Radiation emergency department responsible for reviewing the approving the radiological emergency plan developed by the medical facility to deal with the radiation accident, while considering the requirement of other competent authorities. And we are currently preparing for hospital to receive radiological emergencies. We can see here now, back please. Yes, we can see here we have sent 11 trainee and 200 abroad training. Also for locally training 200. 2 drills we have done, simulated 2 drills, and we provided equipment. We can see it here. It is 22. It is 22 for decontamination kit, and 70 personal dosimetry, and 25 from surface contamination, and 5 radiation monitoring identifier here. Okay, next please. The training and education program is responsible for designing and preparing the scientific material for training purpose, and present in the cooperation with authorized institution and accredited center. In addition, this team will distribute the radiation protection instruction booklet plus brochures to the major hospital and primary health care in the regional health affairs. Okay, next please. So here we can see we started from 2008. We had 2 training courses and 90 participants, and 20 in here in 2020 we had 45 training courses and more than 1,700 participants. Okay. Monitoring and inventory of non-ionizing radiation source. This department is in charge of building network cooperation with the competent authorities, inventory and monitoring the use of non-ionizing radiation in health facility. And this section also monitors the health effect of radiation emitting from wireless communication devices. We started in 2002 by laser. Here you can see using medical lasers, and now we have 2 under procedure: the study of the health effect of the wireless communication and the guideline for magnetic imaging resonance. Okay. The last department is quality. This department is responsible for improving the network, the work performance at the radiation protection program in health affairs. It is also responsible for the inspection and monitoring the radiation protection standards application at the health facility. This is to maintain safe radiation practice in the line with the standard of NRRC, Saudi FDA, and SPAHI. So radiation safety officer at health affairs have been trained on component of unified model of quality and institutional excellence. Also, a quality guideline for department policy, procedure, and mechanism for radiation protection have been created to support the transformation project of the public health. Okay. We have participated also to different committee. The first one, preparing the regulatory framework to achieve the objective research strategy and application of the atomic technology in the kingdom. Also planning and revising national radiation protection plan, studying the long-term effect of and the damage causing by nuclear war, establishing the processing and storing National Center of Radioactive Waste to activate radioactive waste management in the kingdom, planning and revising the radiation emergency plan to the Gulf Council, studying the method of dealing with terrorist-made chemical, biological, and logical bomb, updating municipal and technical controlling committee for license to establish a commercial wireless communication infrastructure, revising committee response to the introduction of nuclear energy for peaceful uses in order to comply with the requirement of International Atomic Energy Agency. Okay, next please. We have released 5 reference books. As you can see it here, this is the first one, instruction of radiation protection in the health facility in the Ministry of Health, and 2 for radiation protection, 1 medical management and the other medical response. And here the radiation protection guideline for a health cluster and health affairs. Okay, next please. ممكن هنا ممكن نشوف السباهي assessment show the overall rate of success for each criteria at the Ministry of Health level, and you can see here the radiation safety, more than 80%, and that's very good for us. Okay. The second, it is for the first one is for the Ministry of Health. Here it is in the university and other hospital, military, but it is not a Ministry of Health. You can see also the radiation protection is still around 90. Okay, the next. The next, please. We see, okay. Here for overall the kingdom, the radiation safety is, wallah alhamd, it is in the fairest. So this is good for us. Okay, thank you very much. Okay, thank you.
Thanks, Dr. Musa'ad, for your presentation. I know you were very busy, and I'd like to thank you for your participation. Next speaker is Dr. Mohanna Areb. He's the senior physicist, and he is the head of the secondary dosimetry calibration laboratory at King Faisal Specialist Hospital and Research Center. Please welcome, Doctor.
Thank you. Thank you, Mohammed. Bismillah ar-Rahman ar-Rahim. Good afternoon, everyone. So it's a pleasure for me to first to join CAAX, and thank you very much for inviting me to come. So my presentation will, sorry, we have to, yes. So I will talk this afternoon about the international measurement chain and its role in promoting radiation protection and safety in research, industry, and medicine. I will actually focus on the international measurement chain in terms of calibration, what's going on when it comes to the calibrating radiation detection instruments. And I will start with this funny picture. So, do you want to buy apples? The price is only 2 riyal per kilo. So here is a bag of apples. Okay, but I want to measure it actually, 1 kilogram. And then your scale is showing 900 grams only. It is approximately 1 kilogram, isn't it? So this is what happens in general in the market. When it comes to radiation dose, let's see the same scenario. Do you want radiation therapy? The prescribed dose is actually 2 gray. So here is 2 gray for your patient. Here we have the chance that the patient itself is a medical physicist. Like, so okay, but I want to measure it before receiving the dose. So my dose meter is showing only 1.8 gram. It's okay. It's approximately 2 gray, 1.82. It's the same. No, I cannot. It's 10% lower than the 2 grays. I cannot accept. I was told that I have to accept only 5, plus or minus 5%. So this is actually what happens when it comes to measuring radiation when people are actually exposed to radiation. In radiation therapy, the dose per fraction is 2 gray, and you have to give 25 fractions. So it's 50 gray total dose. If you just give 10% lower, then you underestimate the dose, and then you are not treating your patient. For diagnostic radiology, the DRL is saying that you have to keep the dose at 10 milligray. Here again, you have a problem. And in radiation protection, you have the 20 millisieverts per year. So here again, if you have over or underestimation of the dose, then you are either out, dosing the public or the workers. Okay, so recommended doses and limits are actually based on national and international studies, and then you have to follow this in the different areas. So radiation doses need to be measured. Why? Because first we should comply with the defined dose levels and limits. Secondly, the wrong dose can be a problem, either for the patient, you underestimate or overestimate, or in radiation protection, you are treating cancer if you are exposing the public to the high doses that are not properly measured. And then we need to measure the radiation dose in order for us to keep the exposed I mean, the doses at the required values, and then we need to measure them correctly and accurately. So we cannot do this. We do this only if you have calibrated instruments. So when it comes to radiation measurement, in radiation therapy, we use actually ionization chambers. In diagnostic radiology, we have different types of detectors for general radiography, for CT, for mammography, and for radiation protection, we use the survey meters. All these instruments need to be calibrated. So you have now, we reached the magic terms, calibrated. What is calibration? Calibration is actually the way that you are ensuring that the instrument is functioning properly. You have to check that the instrument is reliable and accurate. Reliability, accuracy, these are two different things that can be checked only if you have a calibration lab. And then you have to check this for all ranges of all the energies that the instrument is supposed to work within. And then you have to ensure that the instrument functions reliably in the dose range specified by the vendor. And then you have to confirm that the performance of the instrument under extreme environmental conditions in which they are certified perform satisfactorily. Okay? So you can do this if you follow actually what we call the international measurement chain. The international measurement chain, this is the chain that you have to follow for the calibration. Any measurement made by the end user, radiation safety officer, medical physicist in the radiotherapy or in diagnostic radiology or nuclear medicine, anyone who is responsible for measuring radiation need to do a measurement with traceable instrument, which means to the high level. I will explain this by exposing what are the component of the international measurements. And we start with the high level calibration laboratory, which are called primary standard dosimetry laboratories. We have about 16 worldwide. You have here an example of National Physical Laboratory in UK, PTB in Germany, National Institute of Standard and Technology in USA, National Research Council in Canada, and so on. We have 16 actually. And you have the Bureau International des Poids et Mesures, which is based in Paris. This is the mother calibration, I say father calibration laboratory, because they are developing the high standards in BIPM and transfer, and they compare with the PSDLs. And then you have at the down level, at the lowest level, are the end users, which are the final users, radiation safety officers and medical physicists and whoever is measuring radiation. In between, we have what we call secondary standard dosimetry laboratories. And they use here in the primary lab, they use the primary standard dosimetry lab. They are not available in the market, but they have to develop their own instruments. In the secondary standard, you have this kind of instrument. We call this secondary standards because they are traceable to PSDL. What happens actually? The end user, if they have enough money, they can send the instrument to PSDL and they get this calibration certificate with the highest, performance with the lowest uncertainty. Some users, they calibrate the instrument at the SSDL, and the SSDL, they trace this, there is a traceability to the primary lab through the SSDLs. Some SSDLs, they calibrate directly to the BIPM. It's costly, but this is very high level calibration. And they transfer their calibration to the end users. But we have a special lab here, the IEA. It is considered as primary lab and secondary lab because they compare their instrument to the PSDS and the BIPM, and then either they can calibrate the end user's instrument directly or through another SSDL. And this is the majority of the SSDLs, they follow this last chain. So we calibrate our instrument at the IEA, and the IEA is calibrating their standards at the PSDLs, and then you have the traceability. Any measurement performed So we are responsible for traceability, SSDRs. Any measurement performed here, doing so, we are sure that the one gray, the unit of gray, measured anywhere is the same. We have a good consistency because we are following the international measurement chain. Any gray that you measure, if you measure any value, it gives exactly the same through the calibration factor or calibration coefficient. So this is what we call the international consistency. If you ensure the consistency, then you are sure that any measurement is given with the corresponding uncertainty, and then you are performing good. Okay. Historically speaking, in 1964 and 67, the IEA with the WHO, they met and they decided to establish the network of SSDRs, and then they this is a group that met in 68, a group of experts coming from it's worldwide group of experts. They met at Venezuela in Caracas, and then the first international code of practice was issued, and then they established the original network of the calibration lab. At that moment, they call it calibration center, regional calibration centers, and later on, it became secondary standard dosimetry laboratory because they are considered as secondary standards. Currently, we have 90 SSDRs world in 72 countries, and they are seconded by 5 collaborating organizations and 16 primary standard dosimetry labs. Okay, this is a map of the labs worldwide, and you can see here in blue and green the SSDRs. They are equally distributed, but we see that these SSDRs are most, often situated in Latin America, in Africa, in some Arabic countries, and in Asia also. So these are the organizations that second the network. We have the ICRU, IEC, IOMP, and so on, and BIPM. They are helping a lot in maintaining the standards at the level of the SSDRs. And you have the 16 primary labs. As you can see, there's no primary standard dosimetry laboratory in Middle East, Africa, and Latin America, unfortunately. I think the moment is now is coming. If one of the Middle East countries can decide to, it's very easy. You need just to link the primary lab to the government because it should be sponsored by the government. Okay, so the secretary of the IEA is based at the IEA at Vienna, and it is actually advised by the SSDL scientific committee, which meets once 2 years. So they study the. And one of these guys here is from Saudi Arabia. It's a high honor for Saudi Arabia to participate with this group. Most of them are coming from PSDRs, from ICRU, and so on. And we have SSDL newsletter that is published twice a year. And in the last issue of the SSDL, the history of the Saudi Arabia SSDL was published there. Okay, and we follow actually the SSDL network charter, which describes the rights, the duties of the members, including the requirement to be a member of the network. The central laboratory of the IEA is considered as the main laboratory, helping the SSDRs. One of the advantages of the network is to offer free of charge the calibration for the SSDRs, and we have radiotherapy, diagnostic radiology, brachytherapy, radiation protection, and just recently they installed one linear accelerator with 8 X-ray energies dedicated just for calibration. So the service hasn't started yet, but they will offer calibration for linear accelerators. So the calibration services provided by the SSDL. I will give the King Faisal SSDL example. So we calibrate ionization chambers, and we have the standard here is a spherical chamber, which is calibrated to the IEA, traceable to the PTB. The radiation protection, so we calibrate digital and analog survey meters. I would say 95% of the activities of the SSDR is dedicated for the calibration of radiation protection. And then we have these personal dosimeters. Any kind of dosimeter can be calibrated following the international requirements. For example, we use the Phantom to simulate the trunk to calibrate the personal dosimeters, and the Rode to simulate the extremity dosimeters and so on. The contamination detectors and monitors, we use the reference sources traceable to NPL. For neutron monitors, right now we do the calibration using the high energy linear accelerator operated at 15 MeV. So you have the generation of the neutron activation. So we compare the response of our standard, which was calibrated in Canada. And if you look at the spectrum of the neutrons generated in linear accelerated at the ISO center, it's similar to the spectrum of the American beryllium, which means you can use the calibration factor actually. This is for radiotherapy calibration. We have many chambers traceable to the PTB, NIST, and IEA. And we have also diagnostic radiology for our general radiology, CT. We calibrate the PEN chambers like this one here. And we have also the mammography since March 2021. We just started calibrating mammo detectors. These are what you call the CMCs, calibration and measurement capabilities. So as you can see, we have all our standards are traceable to the primary lab, either through the IEA or directly to the primary laboratories. Just to give an overview about the calibration for radiotherapy. So we have a Cobalt 16 unit with 2,500 curies. It used to be 5,005 years ago, so now it's decayed. And this is a calibration certificate that we are issuing for radiotherapy with an uncertainty of 1.2%, which is excellent compared to the international level. This is a homemade software that we are using. It calculates the dose rate at any moment, at any distance, with any field size, and also the time, the required time for giving a given dose. This is just for reference irradiation. And this is the uncertainty budget for radiotherapy, which is 1.2%. For ISO 4037, narrow beam spectra, we have 9 beam qualities from N40 to N300. Here again, we calibrate with an uncertainty of 3%. Okay. This is a homemade software that calculates also any quantity, air kerma. Am I good in timing? Okay. And then this calculates the air kerma, ambient dose equivalent, personal dose equivalent, and also extremity personal dose equivalent for any quality. Yeah, this is actually the result of measurement made by one master student from King Saud University. The lady worked for about 1 year. And then you have the diagnostic also. As I said, we have the mammography, RQM since March 2021. So this is a software, Dosidiag, which calculates also the any quantity. Okay, and then these are the calibration certificates for RF, for CT, and here we have the radiation protection. For radiation protection, we have 1, 2, 3, 4, 5, 6, 7 sources of different activities, allowing us to calibrate the instrument at any dose rate range. We calibrate at 3, we're using 3 different activities, and we issue an average calibration factor. This will allow us to check the response of the instrument within the range that it was designed for. And we have very weak Cobalt 16 unit, which is used for calibrating wide detectors that are used for environmental surveillance. For example, nuclear power plant, you have very big 100 liter chambers. You need very weak source to calibrate this kind of instrument. Right now, we haven't used this source. This is the software also, DosiCalc, for calculating also the quantities, the distances, and anything. This is the calibration for radiation for gamma survey meters and contamination monitor. Okay, and this is for neutron detectors. As you can see here, we compare the reference with the dose rate in linear accelerator is about 230 microsievert per hour for 600 monitor unit per minute. And then you see the response, it is correct. So you have a very good response. So now, how to achieve good consistency of those measurements at the SSDRs? You need to, I will finish. So to achieve you need to achieve a good consistency between the labs and between the services. For example, if you provide calibration of those meters for radiation protection, the dose that the TLD is measuring, it should be consistent with the measurement at the lab. So we have many ways. The first way is to, first of all, to check your consistency with the international measurement chain. So we participate to the IEA that sends TLDs, OSL, or radio photoluminescent dosimeters, the SSDS, requesting them to irradiate at a given dose. And then when they evaluate the dose in Vienna, they compare. And then you have the acceptance level, which is 3.5% for radiotherapy, 7% for radiation protection. And they do this yearly. This is an example of certificate for radiation protection. You see here that we have 1.6, and you see down here acceptance of 7% is considered as satisfactory. For radiotherapy, you have 3.5%. Okay, and we got 0.6%. So we do this yearly, allowing us to be sure that we are within the accepted limit. And this is an intercomparison for diagnostic radiology of the chamber. The IEA sent us a chamber. We calibrate it, and they compare with the calibration coefficient established in Vienna. These are, and this is. Secondly, you need to perform the interlaboratory comparison. I mean, you have to for example, to participate, select some labs, calibrate one detector that will circulate among them, and then you compare. This is what we got in 2017. We had we leaded the intercomparison, so we calibrated the chambers, and we sent the results to the Vienna. The chamber was calibrated then there, and then you see the consistency between the calibration coefficients, which is good. It was calibrated for cesium and three X-rays, narrow beam spectra. And the third method to maintain the consistency or to check the consistency is to check the dosimetry services. So you ask the service providers to send you some dosimeters, and you irradiate them at different conditions. Different doses for linearity, different energies for energy dependence, different angles for angular dependence, and a blind test. You just irradiate at a given dose, and you check that they respond actually. So these are how we perform the irradiation. Angular dependence on the left, and then you have the cesium irradiator for linearity, and you have the X-ray. And we use the phantom. You see here the phantom because you have to simulate human body, human joint. And these are the results that we got. And we have in 2017 also we had to organize this intercomparison. We asked the people to send from Jordan, Kuwait, Lebanon, Oman, Saudi Arabia, United Arab Emirates. Saudi Arabia, you need to be sure that we were really strict because we asked the dosimetry service, which is situated in our department, to be really blind to the irradiation. And we got this. I removed because we are asked not to disclose the results, but we removed but in the x-axis you have the participants, and then we use the trumpet curve to check that you have. The results are considered as consistent if they are within the trumpet curve. the lower the dose, the higher will be the level that you are accepting. For example, here for 0.5, it's about 60%. Yeah. And also, with that, I will conclude my presentation. Thank you very much. If you have any questions, yeah.
So we do have one question.
Can you put in? I don't hear. Okay.
Yeah, so we do have one question. For dose calibrators used in diagnostic nuclear medicine departments, do you have any recommendations on how to calibrate and trace the calibration factor?
Sorry, please.
For diagnostic medical medicine departments,
Yes.
do you have any recommendations on how to calibrate and trace the calibration factors for those pieces of machinery, for the dose calibrators?
Those calibrators?
Yeah.
No, yeah. Yeah, right now, we don't have the service for the nuclear medicine, for nuclear medicine dose calibrator. For the calibration of the dose calibrator, you need to use the mainly three sources: cobalt-59, barium, and cesium. And then we are actually planning to, in the future, to, because we have many departments in the kingdom asking for calibrating those calibrators. The first problem that we are facing with that is that you need to do the calibration on site, because those calibrators are fixed with the equipment. So you need to move to go and perform the calibration. The nuclear medicine department, they may do their own quality control using these sources, because they have the reference sources with the given activity in a given date. They need just to measure, and you don't need to calibrate the dose calibrator. You need just to perform the quality control, periodic quality control. But we are thinking about establishing even for nuclear medicine, a calibration service in the future, inshallah. Thank you. Yes.
Okay, thanks, Dr. Mahanna. It's very nice presentation, and we are all actually proud of this SDD lab. It's something that without it, I don't think radiation protection and licenses can be issued. It's otherwise we have to send this abroad and probably waiting a long time, and a lot of things might get delayed. I have just a general question: is do we have another provider separate, like doing the calibration in Saudi Arabia? This one thing. The second question: how much load you have in your secondary lab? I mean, do you have lots of customers? I mean, that's a heavy duty or something that.
The first question, what? Can you repeat?
Yeah. Do we have another calibration lab in the kingdom?
Yes. Yeah,
because I've heard someone in Caxt or maybe some other places, but are not in operation.
Yes. We have actually in the kingdom, we have the Caxt, King Abdulaziz.
Yeah, City
for Science and Technology. We are working actually in close cooperation with our friends in Caxt. They are actually providing the calibration for radiation protection. Mm-hmm. Yes, unfortunately, we are sharing one national project, which is SAO 007. This is an IEA project which started about 3 years ago. So we within that project we were supposed to share the calibration in the kingdom. They are asking to join the network. The IEA is considering that possibility. Unfortunately, the network, I mean the charter of the network is to have only one calibration lab in the country, belonging member of the network. They have only few countries like China. They have it's a huge country with a huge workload.
So one calibration lab will be enough for the country, and you are not allowed to have another one. That means?
Yes. Yeah. Now the CACs can still perform the calibration. They are recognized by the IEA, But now the IEA is studying the proposal to join the network as a second lab. They are doing well because they have very nice equipment, nice irradiators. They have X-ray for diagnostic and radiation protection. I don't think that they started already calibrating X-ray, but they do the gamma. They have a neutron irradiator, but it's out of service. They're trying to repair it. A very nice irradiator. Okay. Now, in terms of workload, I can tell you that in King Faisal, we are calibrating around 1,400 instruments yearly for radiation protection, and just few diagnostic. But it's and now the number is growing because now the regulation is changing, and you have to do it yearly, which means you never it never ends. Yeah. Okay. يعطيك العافية. السلام عليكم. Thank you.
Thanks. Thanks, Dr. Muhanna, for your presentation. And all right, I think we have reached the end of the webinar. I'd like to thank all the audience for joining us, and also I'd like to thank our invited speakers for taking the time and the efforts to participate in this webinar. Before I close, I'd like to thank a few people. I'd like to thank Eric Talley, our HSE director, for his continuous support and for facilitating all means to hold this webinar on time. Also, I'd like to thank our financial manager, Noof As-Saleh, for her generosity and financial support for this webinar. Also, I'd like to thank Marcus Agler, our acting manager, for his assistance and helping us organizing this webinar. And two special heroes, Lamont Jones and Venkata. They are the hero of this webinar. Actually, they took the effort and the time to organize everything you see for this webinar. I'd like to thank them and appreciate all things they have done to have this webinar to be successful webinar. Thanks everyone, and I hope you enjoy the weekend. And hopefully in the future we see you here in KAUST in another meeting, inshallah. شكرا. مع السلامة.